किती लोक पार्टिसिपंट्स किती आहेत?
45 आहेत.
पहाटे 6:30 तिथे
करूया मग. संध्याकाळ झाली.
Yeah, Professor Dani, shall we start?
Yes, it's 4 o'clock. Certainly, yeah. Let's
Okay.
begin the second day session, third
Okay.
session. Yeah.
Okay, so welcome everyone to the second day of programs. We have 2 sessions as we had yesterday. Very interesting line of speakers. Our first speaker is Professor Hee Oh from Yale University, and she will speak on unipotent flows on hyperbolic manifolds. So Professor Oh, it's over to you. Over to you now.
Okay, thank you. I hope you can hear me clearly because my mic actually, I don't hear actually very loudly.
No,
can you hear me clearly?
It is extremely clear. Yeah.
Okay, great. Okay. Okay, so. Yeah, so first, I'd like to thank the organizers for inviting me to speak on this delightful occasion, and happy birthday, Raghunathan. So, yeah, of course, Raghunathan made many important contributions in mathematics, but I think one can say that actually his conjecture on topological rigidity for unipotent flows on homogeneous spaces has basically started this area of homogeneous dynamics. And this conjecture also had a tremendous influence on my own research. So as well known actually, so this conjecture now fully established by Marina Ratner. So it has had many striking applications, and beginning with the proof of open-line conjecture by Margulis. So today actually, so I want to discuss actually one geometric implication of this conjecture on horocycles on closed hyperbolic manifolds. And then I'll try to present a class of infinite volume hyperbolic manifolds where we have a similar topological rigidity theorem. Okay, so I'll begin with actually very simple classical theorem about lines in the torus. So by torus here, 2 torus is simply R2 divided by Z2, so the integral lattice. So, I mean, clearly we have this quotient map from R2 to T2. And by line in the torus, I simply mean the projection of a line in R2 under this quotient map. Okay. So in R2, of course, all the line is closed. It's just a line. But now if you go to the actual projection, then the theorem says that some lines are either, I mean, any line is either closed or dense in this torus T2. And this is known as Kronecker's theorem in 1884. And we can actually say even more precisely. So whether the line is closed or dense, it is precisely determined by the slope of line. If the slope is rational, then the line projects to a simple closed curve in T2. And if the slope is irrational, then we get this dense object in T2. I mean, this statement and the proof is very simple because the symmetry Z2 is very simple to understand. So now we can also go to higher dimensional picture for this. So again, if you consider now n-dimensional torus, which is Rn divided by Zn, then again, like we can consider the line in this torus, which is again the image of a line in Rn to this Tn via the projection map. And now actually, so it's not true anymore that we have a closed or dense dichotomy, but however, the close of every line is a subtorus in Tn. So it's a very nice object. Okay. So this is very classical and then easy to prove. And then the easy to prove is because actually the Zn is not, I mean, abelian group is very simple to understand. So now I want to discuss actually similar phenomenon now for hyperbolic surface. Okay. So to discuss hyperbolic surface, so I want to use this a half space model, a half plane model. So my H2 is going to be just above the x-axis. So it consists of x comma y with a positive y. And then the hyperbolic metric in this half plane model is the Euclidean metric divided by the y coordinate here. Okay. So here, now we consider these horizontal lines. So if I consider the horizontal line, then because the y coordinate is fixed, so if I restrict my hyperbolic metric to this horizontal line, then this line is simply Euclidean line because this y is fixed, so we just get the Euclidean line. So I would like to consider these horizontal lines in this half space model as Euclidean lines. So this is why I wrote Euclidean lines in hyperbolic plane. So these Euclidean lines in H2 are also called horocycles. Okay. So now, what is hyperbolic surface? So hyperbolic surface is simply complete. So when I say hyperbolic surface, it will be always complete hyperbolic surface. And complete hyperbolic surface can be presented as the quotient of H2 by a discrete subgroup PSL2R. Okay? Because PSL2R is an isometry group of H2. So any hyperbolic surface can be presented as H2 over gamma. And S is closed precisely when gamma is a co-compact lattice in PSL2R. So that we have the quotient surface, a compact surface. Okay? So now I have a closed hyperbolic surface S, and by a horocycle in S, that I simply mean the projection of this horizontal line or horocycle in H2 under this quotient map. Okay. So the question analogously as before. So what are the closures of these horocycles in S? So this is a well-known theorem of Hedlund in 1936. So whenever we have a closed hyperbolic surface S, any horocycle, so meaning the projection of any this horizontal line to this S is always dense. Okay. So this is Hedlund theorem. And I want to remark that, so this is actually very far from being true for geodesics. So in hyperbolic plane, so horizontal lines are horocycles and then the vertical lines are geodesics. But it's very well known that actually in closed hyperbolic surface, the closure of geodesic can be as chaotic as we wish. So there's no way that actually, no way to hope for any kind of topological rigidity for geodesics. So this statement is something very special about horocycles. So, so how did Hedlund actually prove this statement? So instead of looking at the surface, he looked at the unit tangent bundle. So the group PSL2R acts, of course, in H2 by Möbius transformations. And then this action is transitive, but it's not simply transitive if you look at the action on H2. However, if you look at the action of PSL2R on the unit tangent bundle of H2, then this action is simply transitive and transitive. So this gives identification of unit tangent bundle of H2 with the PSL2R. And also the identification of H2 by gamma. So my S is H2 mod gamma. So unit tangent bundle of S is exactly this homogeneous space PSL2R mod gamma. Okay. So now we want to consider this one parameter unipotent subgroup. So consisting of this upper triangular matrix 1T01. Okay. So I said unipotent subgroup. So a subgroup is called unipotent if it consists only of unipotent matrices, and then a matrix is unipotent. It means that all the eigenvalues of this matrix are exactly ones. So of course here these are unipotent matrices. Okay, so here we have a one parameter unipotent subgroup. So what's the relation between horocycle and this unipotent subgroup? The thing is that every horocycle actually corresponds to a U orbit. So let's go back to this picture. So here I have this one horocycle. So if I take any, say, upward normal vector to this horocycle, and then, so I said actually, so T1 of H2 is PSL2R. So this the tangent vector here is an element in PSL2R. And then now if I look at the U orbit of this tangent vector, it gives all these upward normal vectors based on this horocycle. Okay. So therefore, if I understand actually the closure of U orbits on the unit tangent bundle, so this will give us actually this description of the closures of horocycles on the hyperbolic surface. Okay? So what Hedlund proved is actually this stronger version. So what he showed is that for every vector on the unit tangent bundle, so in other words, for every point x in PSL2R mode gamma, the closure of XU is everything. So it fills up actually all the unit tangent bundle. So in particular, this implies that every horocycle is dense, okay, in the hyperbolic surface. Okay, so now I want to consider a higher dimensional version of this Hedlund theorem. So Euclidean lines in closed hyperbolic n manifold. So again, like I want to look at a pop space model of the hyperbolic n space. So now here Hn. So this is the above the plane given by y is equal to 0. So y will be my last coordinate. And then again, the hyperbolic metric on this pop space model is the Euclidean metric divided by the last coordinate in y. So for the same reason, now if I consider any horizontal line, okay, so it has to be a line lying on some horizontal plane. So any horizontal line is a Euclidean line, because if I restrict my hyperbolic metric, the y coordinate is fixed, so it's just a Euclidean line. Okay, so I'll call these horizontal lines horocycles in Hn. And now again, like any complete hyperbolic manifold can be presented as the quotient of Hn by gamma, where gamma is some torsion-free discrete subgroup SO n,1. Okay, so the reason why this special orthogonal group appears is because SO n,1 is precisely isometry group of Hn. And this manifold, this quotient manifold M is closed exactly when gamma is a co-compact lattice in SO n,1, so that I have some compact here hyperbolic manifold. So as before, by a horocycle or Euclidean line in this closed hyperbolic manifold, I mean the projection of this horizontal line or horocycle under this quotient map. Okay, so what are the possible images here? So, so this is a theorem of now Ratner and also proved by Char independently around 1990. So the theorem says the following: if M is any closed hyperbolic manifold, then the closure of any horocycle is always a properly immersed submanifold. I mean, so this is very analogous actually to the case of Kronecker theorem about any line in a n-dimensional torus is a subtorus. Okay, because I can say actually even more precisely. So what are the possible properly immersed submanifold? So we can say even more precisely. So more precisely, the closure of horocycle will be a properly immersed totally geodesic submanifold of M up to some translation. Okay, so if my closed hyperbolic manifold M does not have any properly immersed totally geodesic submanifold, then every horocycle will be dense, as in this picture. Okay, so it's possible that some manifold actually does not have any properly immersed totally geodesic submanifold, then every horocycle is dense over there. On the other hand, if this manifold happens to have some properly immersed totally geodesic submanifold, then this submanifold will contain some horocycles, a lot of horocycles, and then these horocycles, of course, cannot get out of this properly immersed submanifold. They can only be dense here. Okay? That is as much as they can do. And then what the theorem says that these are all the possibilities up to translations. Okay? So the closure of any horocycle is a properly immersed totally geodesic submanifold of M up to translation. So how does one prove this theorem? So this theorem is in fact special case of Ratner theorem conjectured by Raghunathan. So this is the statement of Raghunathan's conjecture made, I think, in late 70s. So let G be a connected linear Lie group. So I just want to think of the matrix group. So I put linear here. So G consists of matrices. So for instance, G can be SLNR or this special orthogonal group SO n,1, and so on. And let gamma be a lattice in G. So meaning that gamma is a discrete subgroup of finite volume. So this homogeneous space G mod gamma has finite volume. So we consider this quotient space G mod gamma, and of course any subgroup H of Gx on this G mod gamma, but we are going to consider connected unipotent subgroup. So again, I think I already said that a subgroup is called unipotent if it only consists of unipotent matrices. Okay. Then here's a statement of Raghunathan's conjecture proved by Ratner in 1991 in full generality. So for every x in G mod gamma, the closure of xu, the u orbit of x, is a homogeneous space of another Lie group containing u. So the closure of xu is equal to xh for some connected closed subgroup H containing u. Okay. So yeah, so this is the famous Raghunathan's conjecture. So I like to say that actually, so it's not very hard using ergodic theorem to prove that. In fact, for almost all points x in G mod gamma, the u orbit is dense in G mod gamma. So in particular, the closure of xu will be the all of G mod gamma. But however, actually, the power of this conjecture and theorem is about actually, this conjecture describes the orbit of every point. So under U action. Okay. So this almost all result does not describe actually the behavior of a very specific point given. But however, this conjecture lists all the possibilities. Okay, so Ratner proved this conjecture using her measure rigidity result. But before Ratner, actually, some important special cases were proved by Magoulis and Dani Magoulis and Shah using topological approach. So I want to mention that. And now the special case of this theorem, how is this related to the behavior of horocycles? So we apply this theorem for the case when G is equal to SON, 1, which is a Lie group. And n is at least 2. Now, so remember, so we had a closed hyperbolic manifold which is of the form Hn mod gamma, and then gamma is a co-compact lattice in SON, 1. Okay, and then this SON, 1 mod gamma, this is actually precisely the frame bundle of the hyperbolic manifold Hn mod gamma. Okay, when n is equal to 2 for hyperbolic surface, the homogeneous space was simply the unit tangent bundle, but if you go to higher n, actually it's more than the unit tangent bundle, it is in fact the frame bundle. Okay? So, but we have actually this nice quotient map from the frame bundle to Hn mod gamma, but this considering this frame bundle is nice because any subgroup of SON, 1 can act on this quotient space by translation. Okay? Whereas actually in the manifold, there's no action except for finite groups. So, I mean, as before, so now every horocycle in Hn mod gamma, this is always covered by an orbit of some one-dimensional unipotent subgroup in SON, 1. And now this Raghunathan's conjecture says that the closures of this XU, these are nice manifolds. So therefore, the closure of horocycles is also nice manifolds. Okay? So this is how this statement about topological rigidity of horocycle is related to this conjecture. Okay, so yeah, so actually, so I said all of this actually to motivate this following question. So my question now is that what about in the infinite volume setting? So Raghunathan's conjecture can still hold in the infinite volume setting. So this is the question. And in a complete generality, the answer is no, because actually it's not very hard actually to find some hyperbolic 3 manifold, for instance, which is a product of which is homeomorphic to the hyperbolic surface times R, which contains actually horocycles with very wide closures. Okay. So in this hyperbolic surface, actually, there is many geodesics with wild closures, and then one can somehow promote these geodesics to geodesic planes, and then these geodesic planes actually will contain some horocycles with wild closures. So in general, actually, so in a complete generality, one cannot remove this hypothesis gamma is a lattice inside the G. But however, there are certain class of actually hyperbolic manifolds of infinite volume, which we call convex or compact hyperbolic manifolds with the Fuchsian end, where we have a similar rigidity theorem for horocycles. So this is what I want to explain now. So for n is equal to 2, actually for surface, every convex or compact surface has function end, and then they are constructed in the following way. So take any closed hyperbolic surface. You start with any closed hyperbolic surface, and then choose some simple closed geodesic. Any closed hyperbolic surface contains infinitely many simple closed geodesic. So take any simple closed geodesic, and then we cut this hyperbolic surface along this simple closed geodesic, and then we'll get this hyperbolic surface with two geodesic boundary components. Okay? So you cut here, and then we get this hyperbolic surface with the two geodesic boundary components. But this hyperbolic surface is not complete anymore. Okay, so to represent hyperbolic surface as a quotient of H2 by gamma, we need to have a complete hyperbolic surface. So I want to make it complete by gluing this function end to each geodesic component. Okay, so because this boundary is this simple closed geodesic AL, so I can glue L times R plus this end component here, and then this hyperbolic surface now will become complete. Okay, so this is what I call convex compact hyperbolic surface with function end. But here, so I gave an example with actually one simple closed geodesic, but we can also do the same surgery with any finitely many simple closed geodesics as long as they are disjoint. So you choose finite disjoint collection of simple closed geodesics, and then cut the hyperbolic surface along this simple closed geodesics. You might just have one, or you can have several hyperbolic surfaces with boundary components. But whenever you see geodesic boundary components, you can glue this function end and make it complete. So then you create this hyperbolic surfaces with the function end, and any convex compact hyperbolic surface of this type. Okay, in dimension 2. Now in higher dimensions, so if n is at least 3. Then first of all, most rigidity theorem says that there are only countably many closed hyperbolic n manifolds, unlike in the surface case. Okay, so we have a countably infinitely many closed hyperbolic manifolds, and some of these closed hyperbolic manifold does not contain any properly embedded codimension 1 total geodesic submanifold, but some will do. So in fact, actually, so there is a infinitely many closed hyperbolic manifolds which contains some properly embedded codimension 1 total geodesic submanifold. So I will take them. Okay, so here is the illustration. So let's suppose this S is a properly embedded codimension 1 total geodesic manifold. And as before in the surface case, we are going to cut along this codimension 1 geodesic manifold and then obtain this hyperbolic manifold with a totally geodesic boundary component. Okay. Then we can again glue this hyperbolic surface times R plus, which we call Fuchsian end, and obtain this complete hyperbolic end manifold. Okay. These are what we call this convex compact hyperbolic manifold with the Fuchsian end. So again, we can do with this actually several geodesic manifolds as long as they are disjoint. So if you have this finitely many properly embedded codimension 1 total geodesic manifold, you can cut along this and then glue Fuchsian end whenever you see the boundary component, and then we get these hyperbolic manifolds, and obviously they have an infinite volume. Okay. So we also say that actually we can also include actually a convex or compact manifold with empty Fuchsian end. And empty Fuchsian end would mean that these are closed hyperbolic manifolds. Okay, so now I can state this theorem. So let n be any convex or compact hyperbolic end manifold. So n is the 2, of course, with the Fuchsian end. Okay, so again, like if it's empty Fuchsian end, it means it's a closed hyperbolic end manifold. And then if it's a non-empty Fuchsian ends, then this has infinite volume. Then the theorem is that the closure of any horocycle is again a properly immersed hyperbolic submanifold. Okay. So more precisely, the closure of horocycle can be itself. So this case did not occur in the closed hyperbolic manifold case, but it can occur in the infinite volume hyperbolic case because some horocycle just can stay in this Fuchsian end. Okay? And then it will be possible. You can have some Euclidean line over here, and then they are closed and same as itself. And then another possibility is that just like in the closed hyperbolic manifold case, the closure of horocycle will be a properly immersed totally geodesic submanifold up to translation. Okay. So we have a complete analog of actually this rigidity of horocycles for this class of infinite volume hyperbolic manifolds. So when n is equal to 2, so this goes back to Darbo's result in 2000. And n is equal to 3. This was a work done jointly with McMullen and Mohammadi around 2016. And for higher dimensional hyperbolic manifold, this was done in joint work with my former student, Minju Lee. So how do we prove this theorem? So just like actually the topological rigidity of horocycles for closed hyperbolic manifold actually was a consequence of Olby closure theorem. So we also prove the statement about Olby closures for the unipotent group action. Okay? So maybe I think the good way to summarize this theorem is that in this setting, we prove that U Olby closures are relatively homogeneous. Okay, so now let me explain this terminology. So remember, so I start with manifold which is compact hyperbolic manifold with a Fuchsian end. Okay, so this means that gamma is a discrete subgroup SO N1, which has infinite covolume, whose associated hyperbolic manifold has this property, it has Fuchsian end. And now let U be a unipotent, connected unipotent subgroup of G, SO N, 1. So in fact, actually, it does not have to be unipotent. It can be any connected subgroup generated by unipotent elements. Okay, so it's the same generality actually as in Raghunathan's conjecture. So you can be any connected subgroup generated by unipotent elements. For instance, it can be SO2, 1. Okay, and then now for every x in G mod gamma, so the closure of X to U intersection with some object RFM, I'm going to explain it in a second, is equal to orbit of XH intersection RFM, where H is some closed Lie subgroup containing U, and this XH is closed. So if we didn't have this RFM, this is exactly the same statement as in Raghunathan's conjecture. The closure of XU is equal to XH, where H is some connected group containing U. Okay, so now why do we have actually this intersection with RFM? Because without taking this intersection with RFM, the theorem is not true. It is false, but actually this intersection with RFM is harmless because actually this RFM, in fact, it's a short for renormalized frame bundle. This captures all the non-trivial dynamics of the hyperbolic manifold. So if one understands this intersection, then one understands everything. Actually, it's very easy to recover what the closure of XU has to be if one has this information. Okay. So, so I didn't explain yet what is RFM, but modulo that, I hope actually this title makes sense. The U-Olby closures are relatively homogeneous, meaning that, so if I look at this U-Olby closure in the ambient space RFM, so I replaced my ambient space G mod gamma with RFM, then in here it is homogeneous. The U-Olby closure is homogeneous. So that's why I call the relative homogeneity. Okay, so now what is RFM? So this is short for renormalized frame bundle. And I think this terminology was first used by Sullivan. So remember I said the G mod gamma can be considered as the frame bundle of the hyperbolic manifold. So instead of these points, we have all the frames in these hyperbolic manifolds. And then when you have a frame, the first vector we always determine geodesics in the hyperbolic manifold. And then the renormalized frame bundle consists of frames with bounded geodesics. So of course, if G mod gamma is compact, then all the geodesics are bounded. So therefore, RFM, renormalized frame bundle, will be all of G mod gamma if it is compact. But if it's not compact, then this RFM removes those geodesics which shoots to infinity. Okay. Okay, but it only captures those geodesics. We don't mean these geodesics are closed, but just bounded. Okay. So it only captures actually the frames which defines bounded geodesics. this is a highly fractal subset in G mod gamma. It's very, very far from being a manifold, but it's a fractal set. But however, this fractal set captures actually all the non-trivial dynamics happening in G mod gamma. So in the infinite volume setting, somehow this is the, in some sense, the right object to look at it. Okay. One can also say that because this RFM is not homogeneous anymore, so that is why some of the main difficulty of actually working in this dynamics in infinite volume space occurs. Is this ambient space is not homogeneous in a sense. Okay, so I think my time is up, even though I had 2 more slides. So I think I finish here. Yeah. Thank you and happy birthday again.
Thank you very much, Professor O. We will take some questions. If anybody has questions, they can open their audio and video. Yeah, Professor Raghunathan, your audio is off. Can you unmute, please?
Yeah.
Yes. No, audio is off.
Okay, yeah. Hear me? Yeah. What I want to know is it possible to characterize elements in gamma which correspond to close geodesics? No, not close geodesics, which correspond to bounded geodesics.
Yes.
No, elements in gamma give you closed geodesics, right? I'm sorry. No,
Right. So element of gamma gives a closed geodesic. We don't look at closed, right? Because there are only countably many closed geodesics, so it's not going to be interesting, but it's a bounded geodesic. Yeah.
But is it possible to characterize bounded geodesics in terms of the group and gamma somehow?
Right, it is hard, right? I don't think, right, I mean, yeah, you can only say in G mod gamma, you look at this orbit of one-dimensional diagonal group, and then if this orbit, you can say that it's the closure, yeah, it's the union of all the bounded A orbits where A is the one-dimensional diagonal group. Can I think of it as the closure? I think it's the same as it's the same as that you look at all the closed geodesics, union of all the closed geodesics. It's not closed, so you take out closure, and I think it's the same thing.
Okay.
Yeah. So in fact, actually, the closed geodesics are equidistributed in this space. So another actually way to characterize this space is the so-called non-wandering set of the geodesic flow, actually. But to be precisely, I have to go to the frame bundle. Yeah.
Thank you.
Okay, any other questions?
Yes, can I ask a question?
Yes, please, Sengupta.
Yeah, I just wanted a clarification. You, in your, towards the beginning, you gave the image of the horocycle. Inside manifold, you said something up to a translation. Now your manifold is already G mod, K mod, gamma. So what is the translation?
Right. I was actually not very precise. So by translation, I meant that actually it's so how do I say? So if I have an element actually which normalizes U, then actually I can move. So it's actually easier to think this in G mod gamma space. So whenever you have some object that that U preserves, you can always move this object by the normalize of U, and then U is going to still preserve this object. So that's what I meant by translation. But in terms of manifold, it is the same as that. It's an equidistant actually translation of this geodesic submanifold. So I fix some distance t, and then I move this object by distance t everywhere. Then it's not going to be geodesic anymore, but it's going to be some manifold which is still preserved by U action above. So that's what I meant. Yeah.
Yeah, and what about the situation for complex hyperbolic space? I mean, if you work with SUN1, all the questions make sense, right?
Yes, I mean the Raghunathan's conjecture Ratner theorem. This is completely general. So
I'm talking about space,
right? Any one-dimensional U orbit has still very nice closures, but yeah, we don't have an analogous theorem for infinite volume case. Yeah.
Okay, okay.
Yeah, in some sense, this, I mean, the codimension one total geodesic submanifold actually, this plays very important role, not only in the statement, but also in the proof. And then, but somehow in the complex hyperbolic manifold, I don't think there is a, yeah, codimension one total geodesic submanifold. So,
Okay. Yeah, because probably they become complex themselves. So,
right.
yeah. Okay, thank you.
Thank you.
Okay, any other questions?
So I have a quick question. For convex compact, can one relax the condition of having Fuchsian ends to quasi-Fuchsian ends, or are they counter examples?
Exactly. So thank you for asking that question. So that was actually my last two slides that I didn't have time to discuss. So yeah. So right. So we have a Fuchsian end, and then for hyperbolic 3 manifold, when n is equal to 3, there's a huge deformation space of this manifold. So which gives the hyperbolic 3 manifold with a quasi-Fuchsian end. Okay, and then for n higher, it's known that there is no such a thing. There's no local deformation by a theorem of Kirchhoff-Stone. And now, so we also, with McMullen and Mohammadi, we also proved this rigidity theorem for this convex to compact hyperbolic 3 manifold with quasi-Fuchsian end. But this time, actually, it's not about the horocycle, but our theorem is about the geodesic planes. So, yeah.
I see. Okay, thanks.
So geodesic plane corresponds to the orbit of PSL2R, and then we showed that actually any geodesic plane is either closed dense if you look at the interior of the convex core. And then in fact, so we had a question whether one can replace this interior of the convex core by the total manifold, but it's not true by the work of Yonggu and Zhang. He showed that actually interior of the convex core is the right thing to look at in this rigidity theorem, because there is a counterexample if you replace this interior of the core by the core or by the whole manifold. Yeah. So it's quite interesting because in the hyperbolic 3 manifold case, this rich theory of, this hyperbolic 3 manifold gives us actually this continuous family of this 3 manifold with quasi-Fuchsian end, and then all this, Raghunathan's conjecture, like at least, beyond the PSL2R, you only have countably many actually lattices in each group. So all this theorem applies to only countably many family of lattices, homogeneous spaces. But for hyperbolic 3 manifold, in fact, it's surprising that we can prove this rigidity theorem like Ratner's, or as in Raghunathan's conjecture for this continuous family of hyperbolic 3 manifolds. So yeah. So I felt like this was a very nice juncture between homogeneous dynamics with this low dimensional topology.
Okay, thank you.
Thanks for the question. Yeah.
Okay, is there any other question? Okay, if not, let us thank Professor He Ho from Yale. It was nice to have her very interesting talk. We have the next talk in a few minutes, so don't go away. Thank you very much, Professor. Yeah. Okay, Radhika, are you there? Can you share your slides?
Yeah, yes, I'm here.
Just click on share screen. Yeah.
It is visible?
Yes, of course. Yes, very good. Yeah. We will start in 2 minutes.
Yes.
All right, we will start our next talk. This is given by Dr. M.M. Radhika from Tata Institute of Fundamental Research. I think Radhika was the last PhD student of Professor Raghunathan. Yeah, it's nice to have her speak in this conference, and she will talk on congruence subgroup problem for groups of inner type AN. So over to you, Radhika. You have 30 minutes.
Yeah, thank you very much. So I'd like to thank the organizers for giving me this opportunity to talk in this conference on the occasion of 80th birthday of Professor Raghunathan. I will take this opportunity to wish him a very happy birthday. So today I'll be talking on congruence subgroup problem for groups of inner type AN. This is a joint work with Professor Raghunathan, which grew out of my doctoral dissertation. The talk is divided into 3 parts. So we begin with a problem formulation, and we'll glance through some developments of the problem with regard to a conjecture by Sayre. And in particular, we'll be looking at anisotropic groups of inner type AN, which will occupy the latter half of the talk. So let's begin with the problem formulation. We fix a few notations. K will denote the number field. V will be a set of inequivalent valuations of K. Bf will denote the non-Archimedean valuations. Infinity will denote the Archimedean valuations. S will always be a proper subset of V, which contains the Archimedean places. OS is a ring of S integers comprising those elements in K which are integral outside S. G will denote a linear algebraic group defined over K. I will also occasionally mention it as a K group. We fix an embedding of G in GL and C, so that the ring of S integers is given by the intersection of GK with GL and OS. And for a non-zero ideal A in OS, GA will be the kernel in GOS of the map reduction modulo A. And so it's clear that GA is a subgroup of finite index in GOS. It will be called as a principal congruence subgroup of level A. Now, S congruence, a gamma subgroup of a subgroup gamma of GK will be called an S congruent subgroup if it contains GA for some non-zero ideal A as a subgroup of finite index. Gamma will be an S arithmetic subgroup if it is commensurable with GA for some non-zero ideal A. Now, it is important to note that these notions are independent of the embedding that we have chosen. The lemma here asserts precisely the same. So it basically states that under K morphism of K groups, the inverse image of an S congruent subgroup is an S congruent subgroup. Similarly for S arithmetic subgroups. We look at the formulation of the problem given by Sayre, so that we introduce 2 topologies on GK. One is the S congruence topology, where the fundamental system of neighborhoods of identity is given by the collection of S congruent subgroups. Similarly, one has the S arithmetic topology, and we denote G hat SA as the completion of GK with respect to the arithmetic topology, and G hat SC will denote the completion with respect to congruence topology. And because the S congruent subgroups are arithmetic subgroups, one has that the congruence topology is weaker than the arithmetic topology. This gives a, then the identity map of GK extends to a continuous homomorphism from the arithmetic completion to the congruence completion. It turns out that this map is surjective, giving us the following exact sequence. The kernel of this map is what is known as the S congruence kernel, and by construction, GK embeds into both the completions. So this kernel is split, the sequence is split over GK. And it can be shown that this S congruence kernel is trivial only when the 2 topologies coincide. That is when the answer to the congruence problem is affirmative for G. So according to Sayre, the formulation of the congruence subgroup problem is to determine the S congruence kernel for a given S and G. Certain remarks regarding the kernel are in place. We'll need this in the future, in the sequel. So the S congruence kernel is a profinite group. In fact, CS is a functor from the category of K groups to the category of profinite groups. And when S is a subset of S prime, we assume that both S and S prime contains the Archimedean places. Then one can show that there exists a natural surjective map from the S congruence kernel to the S prime congruence kernel. So this implies that in order to prove the congruence subgroup property for G, it suffices to consider in the cases when S is finite. And the third remark is well known that the computation of the S congruence kernel for an arbitrary algebraic group G over K can be reduced to that of an absolutely simple, simply connected group. So henceforth, we'll assume that G is absolutely simple, simply connected. And the last remark is that the S congruence topology on GK coincides with the induced topology of GK under the diagram embodying the group of adelic points. So here AS denotes the algebra of S-A. So it is a restricted product of KV with respect to the ring of integers. And because we assume that G is absolutely simple, simply connected, and S rank G is greater than 0, the strong approximation property holds for G. It basically states that GK is dense in the group of adelic points. So one has the S congruence completion is the whole of the adelic points. Hence, we can rewrite the exact sequence with replacing the S congruence completion with the group of adelic points. Okay, so that is for the formulation. Now we move on to see certain developments of the congruence subgroup problem. So in the K isotropic cases, one has fairly complete results for the S congruence, for the congruence subgroup problem. It is summarized in this theorem. Basically states that when G is K isotropic with S rank greater than equal to 2, then the congruence kernel is trivial if S contains a non-complex place. Otherwise, it is the group of roots of unity in K. So special cases here were established in the works of Bas, Milner, Sayre, and Meniké. They proved it for SLN and greater than equal to 3. Matsumoto considered split Chevalier groups, versus Steven considered non-split groups of classical type. And around this time, Sayre also studied the group SL2. So Raghunathan proved it for K rank 1 groups, and he also gave a uniform proof for a general isotopic group. And coming to the anisotropic groups, the first result was given by MSR for spinor group of F, where F is a quadratic form in more than five or more variables. This was extended to that of classical groups by Tominov and Rapinchuk, and certain exceptional groups were also dealt with by Chernosov, Platonov, and Rapinchuk. So all these developments are given in detail in an exquisite survey article by Raghunathan and also too by Rapinchuk. Now we look at the conjecture by Sayre, which is relevant to the congruence subgroup problem. So it basically states that if G is a absolutely almost simple, simply connected K group, and such that G is KB isotropic for all non-Archimedean V in S, then the S congruence kernel is finite if S rank is greater than equal to 2, and it is infinite if S rank is equal to 1. We will confine ourselves to the case where the congruence kernel is finite, that is when S rank is greater than equal to 2. And as seen before, this conjecture is completely settled when G is K isotropic. The complement of S is the place is precisely the place where G is KV anisotropic. The Sayre's conjecture is nothing but the Margulis-Platonov conjecture, which gives the normal subgroup structure of GK in this case. So the conjecture states that for every non-central normal subgroup of GK has a form N is delta inverse U, where U is an open normal subgroup of GS0 in the daily group, and delta is the diagonal embedding of GK in GS0. So this, the Margulis-Platonov conjecture is kind of completely settled for the isotropic case. It coincides with the Nesati's conjecture, which is completely known, and Philip Gill has kind of provided a uniform geometric proof for the same. And in the anisotropic cases also, it is known for many of the groups except the outer type AN, the trialtic groups T4, and the exceptional group E6. The contributions here are by Borovoy, Chernosov, Margulis, Platonov, Suri, and Tominov. I have reserved the contribution for inner type AN until the next slide. Okay, now coming to anisotropic groups of inner type AN. These groups can be realized as known elements of finite dimensional division algebra over K. In this case, the set S0, where the group remains anisotropic, are precisely those places where the division algebra B tensor KB remains a division algebra. The Margulis has this result that it is a quaternion division algebra over K and G is SL1K, then the MD conjecture holds for GK. This includes all the anisotropic groups of type A1. And now come back to the Margulis-Platonov conjecture. This is also proved for anisotropic K groups of inner type AN by the work of Raghunathan, Rapinchuk, Potapchik, Segev, and Seeds. There have been certain recent developments for the groups of inner type AN with regard to the SAYS conjecture. One is by Prasad and Rapinchuk. For this, we need to state the following definition. If K or K is a Galois extension and sigma is an element in the Galois group, then a generalized arithmetic progression is a set of valuations, non-Archimedean valuations, V in VF, such that K is unramified at V and the probability element belongs to the conjugacy class of sigma. And Prasad and Rapinchuk recently proved that if G is K an isotropic algebraic group of inner type AN, and S is a generalized arithmetic progression disjoint from S0, then the S congruence kernel is central and in fact trivial. My work with Raghunathan also deals with K anisotropic groups of inner type AN, AD-1. So we state that if S has a certain property which we call as being the D-amenable set, such that GKV is non-compact for all non-Archimedean V in S, then the S congruence kernel is trivial. As a corollary, we obtain that the kernel is also trivial in the complement of S is a finite set containing S0. Now, I'll define what the D-amenable property is. So here D is a positive integer, and let S be a subset of valuations and W be the complement of S. If there exists an integer H greater than 1 such that for every extension K over K of degree D, the quotient KW plus mod K bar star has exponent dividing H, then we say that S has D-amenability property. So here KW plus is the quotient of the W ideals modulo identity component, where W ideals is the restricted product of KV star with regard to the units, and K bar star is the closure of K star and KW plus. One can define the exponent of a D-amenable set S as the GCD of the exponents of KW plus mod K bar star, where K runs, capital K runs over all extensions of degree D. And we show that a generalized arithmetic progression is in fact a D-amenable set. Even if you throw out the Dirichlet density 0 set, it still remains D-amenable. What is desirable is to show that any finite set S containing the Archimedean places and which is disjoint from S0 is D-amenable. And together with the theorem here, one has the result, one has SAYS conjecture for groups of inner type AN, anisotropic groups of inner type AN. Now we look into a few methods of proof. A common strategy of proof seen in many of the anisotropic cases is, that there are two steps. One is to show that the S congruence kernel is central in the arithmetic completion. And once you have the centrality, then it can be shown that the S congruence kernel is a contact interval of the kernel of the map H2GAS Q mod C to H2GK Q mod C. Here the left side has continuous cohomology and the right side has a group cohomology. And this kernel is in fact what is called as the metaplectic kernel. And it is known to be finite always. And this metaplectic kernel is completely determined, and hence so is the S-congruence kernel when it is finite. So it is shown that S-congruence kernel is either trivial or a group of roots of unity. This is dealt with in complete generality in the works of Prasad Raghunathan and Prasad Raghunathan. There is no standard way of proving the centrality of the S-congruence kernel. However, one method which kind of works for all isotopic groups and also certain anisotopic groups is this is given by this proposition. So that if G is defined over K and such that for every V naught in S, there is a subgroup GB of G hat SA of the arithmetic completion such that it maps onto GKV. Remember that the congruence completion, we identify the congruence completion with the group of the adelic points, and GKV sits inside this group GAS. And the next point, the next point is for V1 not equal to V2, we need GV1 and GV2 to commute element wise. And the third condition is that the subgroup generated by GV is dense in the arithmetic completion. Then CSG is central in G hat SA. So this result, using this result, Prasad and Raghunathan in their recent work establishes the centrality of the kernel for G equals SLA and greater than or equal to 3. In fact, in an earlier work, Raghunathan has proved that the same argument can be used to prove centrality of the congruence kernel for K groups with K rank greater than or equal to 2. And Raghunathan proves this using this result, simplifies the proofs of centrality of some anisotropic exceptional groups in one of his works. Now we look at a proof of our approach to prove the triviality of this congruence kernel for when SST amenable is slightly different. So here we begin with looking, considering the centralizers of elements of the S-congruence kernel, the centralizers considered in the arithmetic completion. And the crucial point here is the fact that the image of these centralizers maps onto a subgroup of finite index in the congruence completion. So this is the content of the proposition given here. It basically says that when SST amenable with exponent Q, the centralizer has the form omega x times G, the adelic points K, of GKW S0, W minus S0, where omega S is a subgroup of finite index in GK S0. One then considers the abelianized kernel. So going on with the commutator of CSG, one has the following exact sequence. And using the proposition, it can be shown that the centralizer of CSG prime, considering the arithmetic completion mod C, is a subgroup of finite index in the S-congruence completion. Now, this kind of helps us to show that the S-congruence kernel, using the MP conjecture, one shows that this following the given extension here is central, and then from the works of Prasad Raghunathan and Prasad Raghunathan, one can conclude that the kernel here is trivial. So one has that CSG prime is trivial. Yes, and this shows okay. The triviality of CSG prime is that CSG is perfect for S whenever SST amenable. Now the S-congruence kernel is profinite, and if non-trivial, it should admit a finite simple quotient. So we show that the S-congruence, and we prove that the CSG in this case does not admit a finite simple quotient. Hence, one has the result that when SST amenable and S and does not intersect the set S0, the S-congruence kernel is trivial. Okay, I think I'm done here. And here are a couple of references. In the last three are survey articles, which includes which are expensive survey articles. And here, the last two words are the recent developments on groups of inner type AN. And the computation of the metaplectic kernel is given in Raghunathan's paper, Prasad Raghunathan and Prasad Rapic's paper. Yes, I think I'll stop here. Thank you.
Thank you, Radhika. We will take some questions. Please unmute yourself. You can ask questions. Okay, I don't see any questions. So thank you very much, Radhika.
Thank you.
Yeah, we will resume at 5:20. The next talk will be at 5:20 by Professor Kai Uwe Bucks. So we take a break. Yeah, please come back at 5:20.
हेलो ये नहीं खाना ये खाने प्रिशा ये लो चल
Hello, Professor Box.
Yes, hello.
Yeah, welcome. I'll be chairing the session. I'm just looking at your slide. It is not in the center of the screen.
That is correct. That will facilitate keeping track of past slides. So
Okay,
the screen will fill.
Okay, okay. Later we will see. All right. Yeah, it's interesting. I must learn this. Yeah.
We had quite some time to practice during these online course things. So the epidemic has taught me a lot.
So you can display the previous slides somehow on the same screen.
Yes, that's just taking a screenshot of the current window and placing it automatically where there is place available on the screen.
Okay. All right. That is interesting. Yes. Yeah, I generally keep two windows. That is same file. I display two pages one by one.
Yeah.
Keep changing the previous page. This is all that I can do, but this is interesting technique. Yeah.
Trying to emulate Blackboard talks as much as technically feasible.
Right. So your current semester is online?
Yes. And the next term, they're going to try some hybrid stuff. Probably that will be a lot more work for everybody.
I see.
But hopefully we get back to normal operation like next summer.
You mean people will lecture in the classroom, but some students will be online?
Yes, exactly.
So situation is not uniform in various areas of Germany as far as COVID is concerned?
It's not by area, it's more or less by university.
Okay.
I mean, the states have different regulations, but there is always some flexibility and universities can be more or less aggressive.
So the university will partially open to students who are vaccinated or those who want to return?
That's the current discussion. Currently, we are only open for classes that cannot be taught online, like sports or lab classes in chemistry.
Okay.
But next term, that will change and hopefully it gets back to normal operation. We should start, I guess.
Yeah, it is almost time. Yeah. Okay, so welcome back. Next talk is by Professor Kai Uwe Bucks. I hope I'm pronouncing your name correctly, from University of Bielefeld. And he will speak on an alternative construction for the boardification of outer space. So over to you, Professor Bucks.
Thank you very much. First order of business, I have to apologize for my video being offline. I don't want YouTube to know what I look like. I ask for your forgiveness. Second order of business, I'd like to congratulate Professor Raghunathan on the occasion of his 80th birthday. It's a tremendous honor to be a speaker at this conference, and I thank the organizers for inviting me. 1968, Invenciones published a paper by Professor Raghunathan with the deceptively modest title, A Note on Quotients of Real Algebraic Groups by Arithmetic Subgroups. And in that paper, he pushes a more theoretic point of view for reduction theory. At least that's how I think about it. And that point of view has informed much of my thinking. And to some degree, it will show in today's talk. So this is about a boardification of outer space. let me start by giving you the overview. So we will be in this lecture talking about the right side of this slide, OutFN. OutFN is an interesting group, the auto-automorphism group of the free group. In order to understand it by geometric means, one looks at its action on outer space. And Laden Besvina and Mark Fain have given a way to bodify that. This is parallel to the situation for GLNZ or SLNZ. There you look at the action on the symmetric space, and a bodification has been given by Borel and Serre, and an alternative construction has been provided by Grayson. The difference between the Borel-Serre construction and the Grayson construction is Borel and Serre add stuff at infinity. They add a boundary to the space. And Grayson pushes in from infinity, removes stuff near infinity, and what is left is a retraction, an equivariant retraction, deformation retraction. So what I will be discussing is joint work with Peter Smiley and Karen Vogtman, where we mimic Grayson's approach to give another construction for the bodification of outer space. So one thing to keep in mind is the philosophical similarity. So the symmetric space, the way I like to think about it is as a moduli space for tori with a flat metric. And outer space is a moduli space for metric graphs. And the action of these groups is not by changing the metric and moving about in the space that way. It's by changing the way the fundamental group of that object, the torus on the left hand and the graph on the right hand, is identified with z to the n or fn respectively. So that's how these spaces work. So, oops, what happened? There. So first of all, what is outer space? You start with the rows. A rose is a graph that just has one vertex and n petals. So this is a rose. And the free group is just the fundamental group of that graph. And a connected graph has a contractible universal cover. So it's a classifying space for its fundamental group. And that means that the auto-automorphisms of the free group can be described as self-homotopy equivalences of a graph up to homotopy. So these are the homotopy classes of self-homotopy equivalences. And that's the way to describe the auto-automorphism of Fn. And oops, now I'm running out of space for a little bit. Just a sec. There we go. So outer space wants to consist of marked metric graphs. So what is a marking? A marking of a graph is an identification of its fundamental group with the free group. And the way to realize that topologically is to take a homotopy equivalence of the rows to the graph. And a metric on the graph is just a way of assigning length to the edges. Each edge gets a length greater than 0. We will later on vary these lengths, and then it will be interesting what happens if the length of an edge goes to 0. Well, then the edge sort of disappears, and well, that's a collapse of an edge, and that could change the fundamental group of gamma, or it could, or it doesn't, and different things will happen. The volume of a metric is just the sum of all edge lengths, and an isometry of a metric graph is just a graph isomorphism that preserves length. So this is all very natural. A point in outer space, and we will be working with reduced outer space, is a connected, marked metric graph of volume 1. So all the edge lengths add up to 1, and the fundamental group of the graph is identified with a free group. The graph is supposed not to have terminal vertices, so no vertices of degree 1. And it's also not supposed to just subdivide edges, so no vertices of degree 2. And the term reduced refers to the condition that we also don't want separating edges. And now if I have two such gadgets, so gamma is a graph, G is a marking, and mu is a metric, and I have another graph, delta, H is a marking, and mu is a metric, then I need to say when they are equal, and they are equal, so they represent the same point in outer space, if there is an isometry between the two, such that if I look at the diagram given by the markings, so those are maps from the rows to gamma and to delta, that diagram is supposed to commute, but only up to homotopy, because my maps, my markings are also just up to homotopy. Those are equivalence classes, essentially. So that's what a point in outer space is. Oops, now I'm running out of Blackboard space. Never mind. So there we go. Here's a picture. So let's look at n equals 2. So here's the rows with 2 petals. I drew one of them in red and one of them in blue. And here are our metric graphs. So this is a graph with 3 edges. It's a theta graph. You can pretend that all the edges have the same length. So they are all length 1/3. And the labels, the loops, indicate how the homotopy equivalence is supposed to work. And here you have an edge. So here you just have the rows again, but now one of these 2 petals is oriented differently. But because there's an isometry between the 2, those actually represent the same point in outer space. And what you can see is if I take the middle edge here and make it shorter and shorter and shorter, what happens is that I approach this face. So each volume 1 metric on a graph is just barycentric coordinates for a point in a big simplex, right? And since all the lengths are supposed to be greater than 0, this is an open simplex. So outer space is just a collection of open simplices. And what this picture is supposed to indicate is which open simplex arise as faces of other open simplices. And in this picture, there is another thing interesting, namely what happens here at the corner. Well, in order to go there from the triangle, 2 edges have to go to 0 in length, but that would just leave you with the rows with 1 petal, and that has the wrong fundamental group, so it can't be there. So this is a face that is missing in outer space. We think of these as ideal faces or faces at infinity. So this is, and the task of boardifying outer space is to invent stuff that can be glued in there. That's what this is all about. So just a little recap, moving in outer space happens by changing the metric. That's how you move within a simplex. If you change the metric and the edge length of a particular edge tends to 0, you move towards a face of that open simplex. And if collapsing the shrinking edge changes the fundamental group, that face is not actually in outer space. So here is 2 illustrations what happens. So this is what we have already seen. We have a theta graph, and if we shrink one of those 3 edges down to 0, we just approach a face. So here we have changing that. Here you could shrink another edge, and so on and so forth. So moving towards the edges means shrinking one of those 3 edges, but shrinking 2 of those edges, that takes you to infinity because it's no longer there. Here we have another triangle. In this case, we have n equals 3, and the triangle comes from rows. And here, all the faces are at infinity. Because in a rose, if you make one of those petals shorter at the expense of the others, right? And you make it really short all the way. No, wait, just this is not approaching an edge. This is approaching a face. So I should put it there. Even if you just make one edge shorter and shorter and have it go to 0, you're still approaching infinity because collapsing a loop, deleting the loop, will just change the fundamental group from F3 to F2. So that will take you outside of outer space. And the goal of boardifying outer space is to find a co-compact out of n space with finite stabilizers, and you want it to be highly connected at infinity. So it will be highly connected very likely because outer space is contractible, and you want to add stuff at infinity to make it not just highly connected, but also highly connected at infinity. And you want finite stabilizers, right? So in order to make the space resemble the group as much as possible. So that's why the first idea that pops to mind after drawing these pictures won't work. So the first idea is, of course, to add in the ideal faces, right? Then clearly the complex would be co-compact mod the group, and everything would be nice, except stabilizers of ideal faces are not finite. So the stabilizer of a simplex in outer space is essentially the symmetry group of the graph, but the stabilizer of an ideal face, that's in outer space, also allowing you to take a face to a neighbor, to a neighbor, to a neighbor, just as long as you keep the vertex at infinity. So stabilizers would be too big for that idea. That's not a successful idea when it comes to boardifying outer space. So let me tell you what Mladen and Mark did. So you need to be more careful. You need to blow up the vertices at infinity. So here's how they do that. A core graph in gamma is a subgraph that can be written as a union of simple circles, finitely many simple circles. So for instance, in this one, the proper core graphs are, well, these are the simple circles, and everything you can write as a union of those are core graphs. So besides those, that's just the graph itself. And now you can take the open simplex that corresponds to the graph gamma, and you can map it to the product of closed simplices over all parametrized indexed by all the core graphs. And what you do is you take a metric, you restrict the metric to the core graph, and then you rescale it to 1. And afterwards, you take the family of all of those, so the tuple of all of those. And that will be an injective map on the simplex. And you take the closure of its image. And that will be the bordification of this open cell. And then you glue them all together to get the bordification of outer space. Let me show you the picture, what happens. So here's an example. Again, the theta graph. The theta graph is a core graph itself. So the first map is just the identity map, rescaling a volume 1 metric. Well, taking a volume 1 metric on gamma, restricting it to gamma doesn't change it. Rescaling it to volume 1 doesn't change it. So in the first coordinate, we just get the identity. And now we have these 3 other core graphs. And if you look at what the simplex of such a diagon is, well, that is just the unit interval, right? Because, well, what is a point in this interval? It corresponds to well, there are 2 lengths for each of these 2 edges, right? And they have to add up to 1, so you just get the barycentric coordinates of an interval. So that's one thing. And now you have these 3 intervals for each of these core graphs, for each of these circles. You have 1 interval. The product of these intervals is a unit cube, and it remains we still need to understand the map from the simplex to that cube. And here's what rescaling a metric after restricting it to a core graph will do for you. So it takes the triangle and it maps it to this weird surface kind of thing. So you can understand what the edges do. So what does the blue edge mean? The blue edge means the blue, so this side of the triangle is where the blue edge has gone to 0, has gotten very small in length. So the red and the black edge are the survivors, and where you end up on this blue edge is given by, well, how long is the black edge and how long is the red edge. And that will correspond to a point here on this edge, on this edge. So you have this coordinate in the unit cube, but you will be on the 0 face for the blue edge. So you are on the bottom edge down here. And similarly with the red edge, you end up at the top red edge. And this little vertex here that isn't there, the vertex at infinity, this vertex gets blown up to the yellow edge in the cube. And the way this works is, well, when you approach the yellow vertex at infinity, what does that mean? That means that the blue edge and the red edge both go to 0 in length, but they don't need to go to 0 at the same rate. They don't need to go to 0 at the same speed. So if the red edge is always 10 times longer than the blue edge, you will end up at a point up here. Not so sure about that, but anyway, so you will be close to the boundary because the red edge will remain 10 times larger than the blue edge, even in the limit. This is what you keep track of. So this keeps track of the direction in which you approach infinity, the direction from which you're coming. It's like the tangent cone at that point gets blown up. It's a blow up in the sense of algebraic geometry. And that is why this little vertex here gets blown up to an edge, and you would, and it is, it gets you a full-blown hexagon. Actually, I do have, we can see that here. So this gives you an idea of what that surface looks like. And if we rotate that cube so that we get a top view on that surface, you see the triangle gets blown up to a hexagon, and every other edge of that hexagon corresponds to a vertex of the original triangle, a vertex at infinity, and every other edge, those correspond to the finite faces of the triangle. So that's how you can visualize this thingy. So this is very much reminiscent of, maybe I stay on that page a little longer. So this is reminiscent of the Borel-Serre compactification, right? The way you think about this is when you approach infinity, that means a closed loop is going to 0 in length. The metric degenerates in a way that affects the fundamental group. That's the same way that you approach infinity in the symmetric space, right? Where you have a moduli space of flat tori. It means on that flat torus, you find it, you fix a geodesic loop, and the metric degenerates in the sense that that closed loop goes to 0, and that's the way you approach infinity. And the Borel-Serre compactification wants to keep track of various ratios, asking from which direction do I approach infinity? How do I go to infinity? And this Bestlina-Fein boardification of outer space is adding the very same information. It's using the same information to differentiate points at infinity. So that's something to keep in mind. So the alternative construction is inspired by Grayson's approach. Namely, instead of adding stuff at infinity, you want to remove a neighborhood of infinity. And now you have to be a little bit careful. We will just get to that. So how do you remove stuff at infinity? Well, first of all, you look at the infinite faces, and then you say, well, stay away from them. So you add a border saying, I shall not approach infinity closer than that, or closer than that, or closer than that. So that's what you do when you want to stay away from infinity. Now, we already saw that there are actually layers to infinity, right? There are triangles, all of whose faces are at infinity. And then there are vertices at infinity, and there are edges at infinity. And we want to stay away from infinity in a way. We want to shave off material. We want to shave off ideal faces in a way that after shaving off, the remaining solid body remembers that there was something like infinity in this direction. So these two pictures illustrate the difference. So here you shave off a lot from the vertices and far less from the edges. And what that means is, what that results in is that for the vertex, like the top vertex, there is still a face like the green, well, no, green is not good, like the black one right here. This little face, that is a remainder, that is remembering that there was an ideal face in that simplex in that direction. And you also want that happens for the edges. So you want to remember everything. And this only happens when you're careful, because what could happen is that you shave off, say, equal amounts from the vertices and from the edges, but then after shaving off the vertices, everything looks fine, right? But then you shave off the edges, and when you shave off all the edges, the faces that told you the vertices are actually there are all gone. So you shaved off too much for the edges. So you need to come up with a rule that says how much material you shave off for each vertex, edge, two-face at infinity. And it's not too hard to write that down in such a way that if you shave off everything in a simplex, then a permutahedron remains. And that's exactly what we do. And here's a picture for how the construction works for n equals 3. And again, I have a picture that this is now more important because this is again 3 dimensions. So the graph that we're dealing with is this one. So the n equals 3, we have 4 edges. So the barycentric coordinates give us an open 3 simplex in which we move about. And there are 2 infinite faces, 2 faces, and there are 2 finite 2 faces. So you can collapse the green edge and that doesn't affect the fundamental group, and you can collapse the blue edge and it doesn't affect the fundamental group, but collapsing the red or the pink edge will take you to infinity. So oops, what happened? There we go. So this here is a view from the side. The view is you're viewing a finite face. So this is this front face here that now degenerates is a finite face, and you can see the jewel has a face inside that finite face. Similarly, the back, that's the face that degenerates now, I hope. Yeah, that also has a finite face. And the other faces are all infinite faces and they get shaved off. So the edge here gets shaved off, leading to that small quadrilateral. The edge in the bottom gets shaved off, leading to that bottom quadrilateral, and so on and so forth. We call these bodies that remain jewels. And when you are careful and you make your rules about how much to shave off so that everything fits together nicely when you want to glue outer space out of those open simplices, and in this case out of those, and then the jewels are subsets of those open simplices, so you want the gluings to work, and you can do that, and then you get jewel space. That's our alternative to the Borel-Serre compactification, to the Bestwiner-Fein compactification. So, and what happens, what you get is jewel space, and that's an equivariant deformation retract of outer space. In particular, it's contractible. So it's a nice space. What can these spaces be used for? So Bestwiner and Fein proved about their bodification of outer space that it is 2n minus 5 connected at infinity. And that implies that out of n is 2n minus 5 connected at infinity. It doesn't directly imply that because the action of out of n on the bodification is not free, but the stabilizers are finite and out of n is virtually torsion free, and one can go from there. Also, as a consequence, they obtain that out of n is a virtual duality group of dimension 2n minus 3. And this, of course, is essentially just carrying out part of the program again from the Borel-Serre compactification, right? This is what you use the bodification for. The Borel-Serre compactification, wait, I'm going to get to that anyway. So let's see. I already remarked on that. So the point here is that out of n, so B follows from A by means of, so what is that torsion-free normal subgroup of finite index? So if you look at out of n and you project to GLNZ, and then you project to GLN Z mod 3Z, then the kernel of the composition, this is a finite group, right? So the kernel of that composition is a subgroup of finite index in out of n, and it's a classical theorem that that subgroup is torsion free. And for the virtual duality group property, one also needs to know that the virtual cohomological dimension of out of n is 2n minus 3. That's a result by Color and Vogtman. And then you need to understand what the compactly supported cohomology for the bodification, or a free, well, yeah, for the bodification, what that thing is. And you need to know that it's concentrated in dimension 2n minus 3, and you need to know that it's a free abelian group. And these two items, Bestwiner and Fein do via combinatory Moss theory. So what do we add to the picture? Well,
Professor Bucks, the time is over.
Oh, the time is over. Okay, then, oh, sorry about that. Let me just wrap this up. So we add that Rose complex is 2n minus 5 connected, which is a relative for outer space. It's the nerve of the cover of outer space by stars of roses. As a consequence, dual space is also 2n minus 5 connected, and there is a direct proof for that that is a little bit simpler than what Besbina and Fein did. And dual space is equivariantly homeomorphic to their bodification. So actually, this is really just, this is not a new space. This is a new construction of their space. So in particular, this is an independent proof that it is 2n minus 5 connected at infinity. That happens to be simpler. Moreover, dual space is easier to understand topologically. So for instance, these hexagons that I drew in the Besbina-Fein setting, in general, it's not so easy to see that those are even cells, like topologically, like PL balls. In our construction, that is obvious, and showing that these two spaces are homeomorphic is the simplest proof I know that the cells of Besbina and Fein are actually cells. So let me stop here, and I thank you very much.
Thank you very much, Professor Bucks.
Sorry for going over time.
Few questions.
Yeah.
Yes, Mahan?
Yeah. So, yes, this seems to be basically a generalization of this manifold with corners thing for, say locally symmetric spaces and then taking its universal cover. Is that what you're generalizing here?
Yes. Yes.
Okay.
Except that the problem is, of course, that
this is
that
not a
outer
manifold.
space is not a manifold.
Right.
And
right.
And that's why half of the picture is missing. So in the symmetric space setting, you can use this to actually write down a topological source for the dualizing module.
Right.
You get the boundary at infinity, and it's a spherical building, and this wedge of spheres that shows the homology is concentrated in a single dimension, and you see, oh, that the homology of that thing is my dualizing module. But that requires Poincare duality, and we don't have that far.
Right. And could you say a word about, I mean, what exactly is the care that you take? I mean, just sort of heuristically, I mean, the shaving off being around the edges being,
Right. You decrease exponentially.
Okay.
So you shave off epsilon in the vertices, epsilon square for the edges, epsilon cubed for the faces.
I see. Okay, thank you.
Something like that.
Yeah, thank you. Yeah.
Any other question? Okay, I don't see any further questions. So let us thank Professor Bucks for his interesting talk, and we will clap.
Thank you very much.
Yeah, we will take a break of half an hour now, and we will resume at 6:30 again. So see you then.
Beautiful room, Parimala.
Hello, where are you, Enki? I can't see you.
I'm in my office.
I don't see your office. That's also equally beautiful. Hello, Raghunathan.
Oh, hello, Raghunathan.
Yeah, he's muted probably.
Very unusual for him.
Very nice to see you. Yeah. Oh, it's good to see the office.
Yeah.
Nostalgic.
Your office is very good. I like your office.
Apparently, this is not my office. So this is a apartment I have rented
Okay.
for the summer. Yeah.
Okay.
Hey, hello, Rama. How are you? Hello, Raghunathan.
Oh, hello, Raghunathan.
Nice to see you both. I mean, oh, she disappeared, Rama. Oh, it's muted.
Raghunathan, very strange for you. You're muted.
No.
Now it's fine.
Rama could hear you because I have this headphone connected, and then it doesn't. No sound emerges from there, from the laptop. She's now going to. She's going to the other PC. Then maybe she can hear.
Okay. Because I saw a glimpse of her and she disappeared. So happy birthday, Raghunathan. It is so nice.
Thank you.
wish we all were
Happy
together.
birthday.
I mean, we missed the occasion. I mean, absolutely. I mean, it would have been so great to
Hello, Parimala.
Hello, Dani. How are you? Yeah, finally.
Yeah, how are you?
Yeah, all fine. Yeah. So.
Hello, Rama. How are you?
Rama, you are muted. You unmute yourself.
Okay, I have unmuted.
Hi.
How are you,
Rama.
Parimala? How are you?
Yeah, we are fine and congratulations. எல்லாரும் சௌக்கியம். எல்லாரும்
Two grandchildren,
Yes.
What
So
are
2 and a half, 6.5, 8.5, sorry.
Okay.
They are doing their respective duties.
Okay then, yeah.
So, how are you doing?
Okay, getting along. House arrest, mostly house arrest.
So, Raghunathan, did you have this Sahasra Chandra Darshanam yet or no?
Sorry? Thousand moons. Well, in all these 80 years, I have probably sighted the moon less than 80 times. Whether full moon or otherwise.
Okay.
Yeah.
Yeah, that's about this time, right? I mean, it's around this
Come
time.
a little later, I
Right.
think.
It's time.
Sure.
It is time. Yeah.
Oh,
I think it's time.
when I said about this time, I didn't mean.
Sorry, it's not time yet. 6:30 is what we have said.
Yeah.
Sure.
More than 5 minutes to go, it looks like.
Yeah.
Anyway, I am signing off.
Okay, bye, Rama.
Rama's. Yeah, she's probably watching, but just put off the.
Sure. Sorry, Raghunathan, I'm just going to talk of exceptional group. I mean, classical groups. I know you don't like this case by case, but.
No. I mean, it's if you can't do it in general, why not case by case? No, I have nothing against it. In the volume in your honor, I've given a proof case by case about embedding quasi-split groups.
Oh,
okay.
I'm glad because I always feel guilty when I talk in front of you and I just mention just classical groups. However, I want to say that usual Hasse principle for number fields is case by case. It is open to give a proof which is case free.
Yeah. I'm aware of it.
It's one of the challenges.
Yeah. Sure. It's right. I don't know. It's Certainly for number fields, I don't think there should be a case by case.
I know your mindset. I mean, yeah. Prove it next time for the next birthday conference. We can expose your.
Well, I don't know.
I still remember the 60th birthday conference in Tata Institute, you know.
Yeah.
Dani, you were responsible, and I was in some sense.
You were the dean, actually.
Yeah, I still remember that occasion very well. Yeah.
I'm afraid my memory for these things is not so good.
So we still have.
It was my birthday conference, but still there are many things which people tell me which they seem to have completely forgotten. So.
Yeah, we remember a lot that conference.
See. Because of my hearing problem, I have to wear this headphone. Otherwise, I can't make out what people are saying. Hi, Gopal.
Oh, hello, Gopal.
Where is he? I don't see him. Hello?
You see, this screen is strange. You know, different people's things, the pictures appear in different places. So you have to move the thing.
Oh, okay. Okay, I can move along. Hi, Gopal. How are you? I think he's muted.
Yeah, he's muted. Gopal, muted.
Yeah. So I can now hear you, and you can hear me.
Yeah, we do.
Yeah. So I will see you, Parimala, in a day or two.
Sure, we will. So, I'm visiting my grandchildren in New York. So,
yeah.
So that's why this new
Hi,
place.
Gopal. This is Rama here. How are you? How is the family?
We are doing well. It's so nice to see you after so many years. I was going to write a letter today.
Okay, please do.
Yeah, so it's really wonderful. You know, we are with Anup for last 1 month or so.
Okay.
Yeah, in New York, and Indu had a knee replacement surgery here.
Oh,
so
how long ago?
About 3 weeks ago.
Okay, she's progressing well.
She is progressing well. She will come here, Rani Aga. Yeah, so she will say hello to you.
Only 3 more minutes before the session starts.
Yeah, so how are you doing? How are you?
Yeah, okay. We are getting along mostly under house arrest.
Yeah, same
in
here.
these COVID times, yeah.
We have come back to New York after 2 years.
Okay, yeah.
Yeah, so.
Hello.
Hi, Indu. Hi.
How are you?
Hi.
Thank you. How are you? Hello, Raghunathan ji.
How are you, Indu?
Yeah. Just fine.
How are you?
Wish you a very happy birthday, and may you make
Thank you.
And we have missed
Hi,
you.
Indu. Get better soon.
Yeah,
Get better
I'm all right.
soon,
I'm
yeah.
moving around, walking.
Good. Okay, all the best to the family also.
How are you keeping, Rama?
So far, so good.
Very good. Hello, Parimala.
Hello. Nice to see you. After the surgery and looking good.
Yeah, looking good, keeping good. Yes.
Very good. Yeah.
Okay.
Should I start the introduction now or wait for a couple of minutes? One more minute.
2 minutes, I guess.
Yeah. Okay, so it's a real pleasure to introduce is a funny word, Professor Parimala, whom I have known all my life at the Tata Institute. It's very nice to welcome her back to TIFR and to speak about Hasse principle for simply connected groups. She's from Emory University, Atlanta, Georgia, USA. Professor Parimala.
Hello. So maybe I'll share the screen. Is it good, the screen sharing?
Yeah, looks
okay.
Fine to me.
Yeah, okay. So, so indeed, I'm very, very happy and honored to be speaking at this very special meeting in honor of, or to celebrate the 80th birthday of Raghunathan. As Venki says, my association also with Raghunathan goes back a long, long time. Maybe the very first beginning was when I was a graduate student taking his analysis course. And somehow I felt as if I was listening to an algebra course. So, so thank you, Raghunathan, and happy birthday. Okay, so the main theme of my talk is to just highlight the significance of the role of simply connected groups in the context of Hasse principle for number fields and later on function fields. Okay, so what is Hasse principle? This has been mentioned already in several talks before. K is a number field. Omega K is the set of all places of K. And for a place, we denote by KV, the completion of K at V. And so what is Hasse principle? One looks for, given a variety over the number field, one looks for rational points of this variety over K. So whether it admits a rational point, and further on, there are questions about how many rational points, density, etc., etc. One way first to approach this question is to look at whether it has a rational point over the completions. One has a slightly better handle at attacking this question because the completion is Henselian and there are better ways to handle the existence of rational points for a variety. Okay, so to state precisely this question, suppose F is a family of varieties or a field or a number field. We say that the family satisfies Hasse principle if for every variety in this family, if it admits local points at KV for all V in omega, local rational points, then it admits the K rational point. Then we say that this family satisfies Hasse principle. Of course, when you talk of Hasse principle, the first thing which comes to our mind is the classical Hasse-Minkowski's theorem. So it says that a family of quadrics over K satisfies Hasse principle. That is equivalently a quadratic form over Q over a number field K represents 0 non-trivially over KV for all completions V of K, then it represents 0 non-trivially over K. Okay, so quadrics are more special than a general class of varieties. It is homogeneous under the orthogonal group. So, so one may look at the most special families of homogeneous spaces under connected linear algebraic groups. So there is an extensive study of Hasse principle for homogeneous spaces under connected linear algebraic groups over number fields in several decades, last few decades. And of course, I want to just say that Hasse principle in general could fail even for principal homogeneous spaces under connected linear algebraic groups. The typical example, which is an exercise in Cazals and Froelich, the exposé of Tate, I think. You take the normic torus, namely the norm-1 elements in the extension L over Q, where L is the biquadratic extension, Q root 3, root 13, root 17. and you take the space X, variety defined by norm equal to 25. This is the normic torus acts on this. It's a principal homogeneous space under T. And this principal homogeneous space admits a local point at all completions, simply because the biquadratic extension you have taken locally has degree 2. And we are looking at 25, which is a square, which is always a norm from a quadratic extension. However, it is a job to prove that's the exercise that this does not have a Q point. So in general, Hasse principle may fail even for principal homogeneous spaces. However, it was Kneser who brought into focus the context of simply connected groups over number fields while discussing Hasse principle. I really want to highlight this point. He was the first person. I had some discussion with Sayre on this topic, and he says, because he was handling, so he was analyzing the spinor genus so closely or number fields that he came to the conclusion of the following conjecture, which I'll mention next. I don't know, Kneser's conjecture is missing from the slides. So he proposed a conjecture in the in 1960s in the ICM plenary talk. He proposed the following conjecture that Hasse principle holds for semi-simple, simply connected groups defined over a number field. Okay, that is a principal. Hasse principle holds means given a principal homogeneous space under a semi-simple, simply connected linear algebraic group. If it admits a local point, then it has a point over the number field. So some examples of simply connected groups, for instance, SLN, which we all are familiar with, and the symplectic group, the spinor group, and basically this exhausts the list of all classical groups, split classical groups. And of course, we have a list of very interesting exceptional groups of type G2, F4, E6, E7, and E8. These are all the list for split groups. And of course, there are, given we are looking at a number field, so for a general field, there are non-split forms of these groups. And this was already mentioned in the previous talk. So if D is a finite, one example, if D is a finite dimensional central division algebra or a field, SLD is the group of reduced norm 1 elements in D. Then it is a semi-simple, simply connected group defined over K. And it fits into an exact sequence S1 to SLD to GLD, which is the group of units of D. And the map to GM, the units of the base field, is the reduced norm map. So this exact sequence of algebraic groups, it yields by the connecting map an isomorphism of K star modulo reduced norm D star with the Galois cohomology set H1K SLD. And the right-hand side is the set which classifies isomorphism classes of principal homogeneous spaces under SLD. Okay, so any kind of Hasse principle for SLD because of this isomorphism reduces to a Hasse principle for reduced norms, namely local reduced norms are reduced norms. And in fact, this is a theorem which goes back before Kneser. Hasse, Maas, Schilling, they prove that if K is a number field and D is a central division algebra over K, and lambda is a central element, it is a reduced norm from KV for all completions, implies it is a reduced norm from D. And in fact, the condition that it is a local reduced norm is simply at real places, because over finite places, we know that reduced norm is surjective. Every element is a reduced norm. And therefore, this condition is precisely for real places. Thus, okay, the conjecture appears here. So Kneser made this conjecture in the 1960 plenary talk. K is a number field. G is a semi-simple, simply connected linear algebraic group defined over K. Then Hasse principle holds for principal homogeneous spaces under G. And once again, as in the case of reduced norms, if KV is a p-adic field, then Kneser proves that this H1 KG is trivial. or a p-adic, this should be a KV, or a p-adic field, this principal homogeneous spaces are trivial, and hence when G is semi-simple simply connected, and therefore the above condition once again reduces to real places. In particular, if K is a totally imaginary number field, then every principal homogeneous space under G is trivial. Okay, so Kneser made this conjecture after verifying this conjecture for classical simply connected groups. The above conjecture is now a theorem. For it is due to harder for other exceptional groups than E8, and you should see the time scale, and it almost took another 20 years to complete the conjecture for the case of E8, and this result is due to Chernusov. Okay, so surprisingly, or maybe even before going to more general cases, I want to say that I'm just focusing on simply connected groups. There's a whole lot of literature on going forward with looking at Hasse principle for more general reductive or even connected linear algebraic groups, finding obstructions like the Brouwer-Marnin and proving finiteness theorems and so on. For many of these results, this basic Kneser's conjecture, which is a theorem, is basic to most of these further results. Okay, so in the 60s, even before Kneser's conjecture was fully resolved, Sayre proposed the following far-reaching generalization of this conjecture, which is now referred to as conjecture 2. If K is a perfect field of cohomological dimension at most 2, and G is a semi-simple simply connected linear algebraic group over K, then H1 KG is trivial. That is, every principal homogeneous space under G over K is trivial. So the cohomological dimension 2 condition, it simply says that you take the mth Galois cohomology of F with values in a finite torsion Galois module. It shall vanish for all m bigger than or equal to n plus 1. Then you say that the cohomological dimension is bounded by n. Okay, so this conjecture, even before the Kneser conjecture was resolved in full generality. And so maybe sample examples of cohomological dimension less than or equal to 2 fields. Totally imaginary number fields are cohomological dimension 2 fields. And Sayre's conjecture here reduces to Kneser's conjecture. And some geometric examples of cohomological dimension 2 fields. These are function fields of surfaces or algebraically closed fields. Okay, so the first non-trivial case of conjecture 2, namely, is for G SLD, was settled by, when I write SLD, you can as well put SL and D for Norman elements in Mn of D. It was settled by Mercury-Suslin, and this is, they prove that H1K SLD is trivial if K is a perfect field of cohomological dimension less than or equal to 2. That, in other words, by the previous description of this set, the reduced norm is surjective. In fact, they prove something stronger, and this is a consequence of what they prove. And the conjecture for all classical groups were settled by Eva Bayer and myself, and the validity of the conjecture for G2 and F4 was already remarked by Sayre, it holds. And the conjecture even today is open in general for the exceptional groups of type trilitarian D4, E6, E7, and E8. And of course, there are many special cases. I mentioned, for instance, the case of function fields of surfaces or algebraically closed fields. In all these cases, the conjecture is fully settled. Okay, so in this context, I want to bring in the one invariant associated to principal homogeneous spaces and simply connected groups, which was proposed by Sayre, and the construction was due to Rost. So-called, we refer to it as the Rost invariant. This is a cohomological dimension invariant, which takes values in the third Galois cohomology with torsion coefficients Q mod Z2. The vanishing of this invariant certainly is, this invariant certainly vanishes for cohomological dimension 2 fields because this lives in H3. Okay, so this invariant RG from H1 KG to H through, it goes to H3 K Q mod Z2. This is the primary abstraction to the vanishing of tosses and the simply connected groups. And this invariant has a simple description and for SLD, and it goes back to Suslin. So let me say what the invariant for SLD. You take H1K SLD, any element is given by a class of K star modulo reduced norms. This class lambda goes to the following element in H3. Lambda defines a nth square class on which gives an element in H1 K mu n by Kumar, and the class D defines an element in n torsion of the Brouwer group of K, which is in H2 K mu n, and you take the cup product that is in H3 K mu n tensor 2. This is the invariant for SLD. So we'll just come back to the, and in fact, Mercurius Suslin, they prove that this invariant in some sense has trivial kernel. This is very, very important, that principal homogeneous space is completely characterized by its Rost invariant, provided the degree of the index of D is square free. Square free index algebras, the Rost invariant completely determines the tosser. So this is very important, which will come into discussion in subsequent slides. Of course, if D is not square free, the injectivity no longer holds. Okay, so moving beyond number fields, for function fields of curves over periodic or number fields, there are conjectures analogous to Kneser conjecture that have been posed about Hasse principle for tosses and the semi-simple simply connected groups. We shall now discuss these conjectures and some progress towards these conjectures. Okay, first number field. K is a totally imaginary number field. X over K is smooth projective geometrically integrate curve, and F is the function field. FV is just you take the completion of K at V and take the function field of the variety X over KV. This denotes FV. It is the KV function field X for each place V in omega. So the following conjecture was proposed by Kolyutelin. So you take a G, a semi-simple, simply connected linear algebraic group defined over F. Then the Hasse kernel, that is the kernel of H1 FG to product H1 FVG, V in omega, has trivial kernel. Here K need not be totally imaginary. You can take K to be any number field and you take the set of all places. So this Hasse kernel is trivial, is the conjecture. In other words, Hasse principle holds for rational points on tosses and semi-simple simply connected groups over F with respect to this bunch of overfields FV. Okay, so let us look at this conjecture in the case of central division algebras over F. Suppose the index is n, then we know what is H1F SLD purely algebraically. It is just F star mod reduced norms. And so the Hasse principle once again is whether local reduced norms or reduced norms. You have this Hasse map to H1FV, and you have this Rost invariant which goes to H3F mu n tensor 2, which we have explicitly described. And you have the local Rost invariants, on the right hand side. And you have the local to global map from H3F to H3FV on the Galois cohomology. And so the nicest part here is that this arithmetic result of Kato, which says that the map on the cohomology H3F to H3FV is injective. Okay, there's no kernel at the H3 level. And suppose you put in the condition that n is square free, then you get it for free. That by going to this diagram, going to the Rost maps and looking at the local global, we conclude immediately, putting together Kato and Mercurius-Suslin results, that Kolyutelin conjecture, namely Hasse principle, holds in this specific case of SLD with D square free index. So we have the following progress on the above conjecture. Suppose K is a number field, and this is a theorem of Philippe Gilles. So he completely settles the conjecture in the case when the curve is just the projective line. So G is a semi-simple, simply connected linear algebraic group defined over the number field. Then H1 of the rational function field KTG to H1 KVTG, the local one, has trivial kernel. So this is the first known result in this roughly in the general case. And of course, this is using Brouhatics and completely classification free. And there is this result of Preeti and myself. It goes back to Preeti's thesis time. If K is a number field and G is a semi-simple, simply connected linear algebraic group of classical type, here it uses classification over the number field. And X is a smooth projective geometrically integrated curve over K, then the Hasse kernel is trivial. H1kx to kvxg is trivial. Essentially, we prove the result for all classical groups. Of course, G is defined over the base field K. And I don't know whether there are further results in this direction. And so this is all the progress so far as I know about this question of polyethylene. Of course, more general questions are for G, not just defined over K, but defined over the function field. Then it gets more intricate. Okay, so now we move on to function fields over periodic curves. Here, K is a periodic, instead of number field, you go to a periodic field, and X is a smooth projective geometrically integrated curve over K. And you have that now, I mean, when we talk of Hasse principle, we have to talk of what are the local completions we are looking at. We look at omega F, which is the so-called divisorial discrete valuations of F. This was already mentioned in Igor's lecture. So this is the set of all discrete valuations of F, which are centered on various smooth projective models of X over the periodic integers. You take various regular proper models, not smooth models, sorry, it's not smooth, but regular proper models of the curve. And you look at codimension 1 points of these curves and look at all the discrete valuations associated to these codimension 1 points on various regular models. So this is the so-called divisorial discrete valuations. And we fix this omega F when we discuss Hasse principle. One can of course take all discrete valuations, but it is this is more of a geometric nature. So the questions on Hasse principle for homogeneous spaces under connected linear algebraic groups, this has gained some momentum in the last decade with several new conjectures posed in the context and new results coming forth. Also because of certain new techniques arriving on the scene, which I'll explain in the next few slides. Okay, the conjecture first. So after some experiments, Kolyutalin, Suresh, and myself, we arrived at the following conjecture that the same as Kneser conjecture, except now F is the function field of a curve or a curve or a periodic field. K is a periodic field. X over K is a smooth projective integral curve over K, and F is a function field. G is semi-simple, simply connected linear algebraic group over F. Then Hasse principle holds for tossers under G over F with respect to the divisorial discrete valuations omega F. Well, we pose this conjecture after verifying it in several cases, including when G is a quasi-split group. And mark it that we propose this conjecture when K is a periodic field. I just want to quickly mention that you can also pose similar conjectures when K is a complete discrete valued field with arbitrary residue field instead of a periodic field whose residue fields are finite. However, this conjecture fails in general, and I'll come back to this point towards the end of my talk. So it's just a warning that the conjecture was only for periodic fields. It's more of an arithmetic nature. And so what is the progress on this conjecture? So Preeti and Hu, they proved conjecture for all groups of type Bn, Cn, and Dn. And in fact, Preeti proves that the Rost invariant from H1Fg to H3F mu n tensor 2 has trivial kernel in these cases, Bn, C, and Dn. Okay, and she arrives at the conjecture after this and in together with Carto's theorem. And the case of SLD, where D is square free index, once again, we have Carto's theorem as well as injectivity of the Rost invariant. So you would get the same if D is square free index for SLD, that conjecture is true. So these are the cases which were proved some time ago. And there are two cases which were left open in the above discussion, namely the general case of SL, and D, where it is type A and 1. Okay, the inner type AN. That is, so D is a central division algebra over K. And the second is the outer type AN, which is the special unitary group of Hermitian forms over division algebras with unitary involutions. These cases remained open for a while, and however, we are slightly in a better state now. So we have the following theorem of Preeti, Suresh, and myself. The conjecture holds for type AN1 if P is co-prime to, there is always this good characteristic assumption in the solution of all these conjectures. So P is co-prime to N plus 1. Note that P is, what P stands for is that we are the base field K is the p-adic field. That is the P. The residue field characteristic is co-prime to N plus 1. Then conjecture A, a conjecture holds for groups of inner type AN. Once again, repeating the this particular case, it is equivalent to Hasse principle for reduced norms for algebras of index co-prime to P. Okay, and so the next unitary case, still it was open for a couple of years, and this is also settled, thereby settling the conjecture for all list of all classical groups. Conjecture A holds for groups of type AN2, that is outer type AN. That is the case of unitary case, where if P is co-prime to twice N plus 1. All these co-prime characteristics we assume in order as so-called good characteristic case. And it doesn't mean, I mean, probably it's also true in the bad characteristic case, but it needs further work. Okay, so what brought about this the solution in the case of AN1, AN2? Here we have, in fact, we needed some new techniques to develop a proof of these results. And so I'll just mention the techniques we use in the proof of the conjecture in AN1 and AN2 cases. So these are the so-called patching techniques, which have been very well used and in so much work concerning things to do with linear algebraic groups or function fields of curves or general complete discrete valued fields. Okay, so these techniques were developed by Harbater, Hartman, Krashen in the setting of function fields in one variables or complete discrete valued fields. And this is what we use as a key technique in order to arrive at the proof for the remaining two cases. So this will be explained in more detail in Kolyathalin's talk tomorrow. And I also want to mention that the more general question I was general question, namely, if the base field K is not a p-adic field but a general complete discrete valued field, the question whether semi-simple simply connected groups, whether the tosses under these groups satisfy Hasse principle, this still was open a little bit of time since all these positive results were proved for function fields of p-adic curves. It still remained over. Can it go further down? And whether it could be true for more general fields than just function fields of p-adic curves, namely function fields of curves or complete discrete valued fields. And finally, there are examples arrived at even for the case of SLD, where it fails for a more general field. So this will be explained in Kolyathalin's lecture. So indeed, conjecture A is indeed generally for fields of arithmetic type. And also there is a whole bunch of results which I didn't mention, cover the case of projective homogeneous spaces. Namely, even for number fields, following Kneser's conjecture, Harder proves that for projective homogeneous spaces under semi-simple simply connected groups, it doesn't matter, even you can take a connected linear algebraic group, there is Hasse principle. Of course, the key thing is to have the Hasse principle for simply connected groups for principal homogeneous spaces, and then you develop how you are going to prove it for projective homogeneous spaces. And in fact, you have similar results for classical groups for projective homogeneous spaces as well. Since I didn't mention it in the beginning, I'll just, maybe my time is getting over. So I want to say thank you, and I conclude at this point. Thank you.
Thank you very much. And are there any questions or remarks from the audience? Does anybody want to ask any questions? All right. Thank you so much, Professor Parimala. Then we shall meet again at 7:10. Thank you. Yeah.
Very nice, Parimala.
Thank you, Gopal.
Nice to hear again on something which interested me a long time ago.
Indeed, I also started reminiscing a lot these days. So, so I thought this is
Well, we're all getting old. That's what it means.
Exactly.
You're still a long way from reaching my age, but still.
Not a very long way. We are racing. No?
Actually, I am quite there. Raghunathan, I am quite there. And last year, I felt that probably I will not even live. So, things are now very different.
No, now things are good. I mean, so.
Raghunathan, when you become old, you should take the ratio and not the difference. Then it's working.
So, once Abhyankar was giving a talk and he said, I want to propose some new directions, some questions, which I would like some youngsters to get involved. Then he said, stopped a minute. He said, what do I mean, youngsters? It's a relative term.
Sure, of course.
That was really, yeah. So Rama, she left.
A physicist has proposed a formula about who looks old, what age a person looks old to you. So it's 10 times square root of your age. So that makes a person, if he over that age, then he old.
So 90 in this case, Raghunathan.
Yeah, something like that. Yes. So Raghunathan is quite young, So
no, but irrespective of other things, he is always young. I mean,
yeah, of course, very active and very young. Yes. We remember he's taking a bread and walking briskly on Homi Baba Road.
How many minutes you have, Venki? Another few minutes?
We meet again at 7:10. It's now.
What I remember most is we have this Independence Day celebrations, flag hosting. Sometimes it will be also raining a little bit and the children will be taking sweets, and then in TIFR colony. And then Raghunathan and Gopal Prasad, they will not know what's going on around. I would hear them discussing so seriously, mathematics. I was still rather young at that time and amazed by what is going on. And I just remember the scene of their discussions just under the flag while flag hoisting is going on, and those events. Yeah.
Thank you.
Yeah, I also remember in my student days, Raghunathan coming out of his office, maybe 5:30 or 6, his trousers completely covered with chalk. He was probably working on the board.
So I do hope their boards survive for some more time. I mean, I'm not sure.
I'm sure they do. They will. Yeah.
No, many places in the universities, they are replacing it by other kinds. And you're forced probably to lecture in a room with probably there's a whiteboard or no board at all. I mean, who knows?
The time of the 2010 Congress, we had a problem. The conference complex place didn't have boards at all. We neither blackboards or whiteboards. So finally, we had to work on that to get them to provide us with boards.
Right, right.
Yeah.
But of course, already a large number of people did not need boards. They were making this PowerPoint kind of presentation.
Mm. Which
Many
is
people,
more
but-
efficient, but you know.
Hi, Bill. Nice to see you.
Hi.
Yeah, welcome.
Hi.
Thank you. Hi.
Hello.
When was it last that you came to India? Maybe Raghunathan's 70th, was it?
No, I didn't come for that. I was maybe the International Congress in
Oh, yeah.
2010 in Hyderabad.
Oh, yes, we met there. No, did you not come to Raghunathan's 60th, maybe? 60th?
He was. Well, I think he was there for 6 years.
20 years ago. Right.
Yeah, we met in the ICM.
Last night I spoke to one. Right.
Come.
Yeah, I remember
You know, some talk.
flying to Mumbai with John Milson. I spoke to him last night. He said, greetings.
My teacher is here.
I'll try to see if this screen sharing works. Try.
Yeah, my teacher is the last.
Is it time?
Not yet. There is another 5 minutes.
Oh,
okay. Let me just test
Parimala,
it.
you were telling me something about Raghunathan's reminiscences of your this in Raghunathan. You're saying,
Oh, did I?
Okay.
It's also another aspect to forget what you say a few minutes ago. Very typical.
So, Raghunathan, what do you do for this? I mean, do you go for exercise or something? I mean, walk?
I do go. Actually, I'm not. I was in between taking a walk outside, but now all the walking I do inside the apartment. After the rain started, I didn't go out for walks. But maybe I will resume now that rains are not so severe, so I can resume walking. But it's I've not really stepped out of the house except for those walks the last year and a half almost now, except 3 visits to my son's place. That's about it.
Okay.
Okay. Medha Prasad. Anup Shivar Congress. What is her name?
Bill, are you people?
Hello. Hello, Sahar.
Oh, hi, Shahar.
Hi.
Good to see you.
Hello, Gopal.
Hi, I was muted. Hi.
It's okay. Mute karo.
Hello.
Hi, Kaushik.
Hello, Kaushik.
Are you? Hello, Kaushik.
Yeah, hello.
How are you?
Good.
Where are you, in Hyderabad or in Bombay?
Bombay for the last 8 years now, 7 years.
You know, I met you in Parimala's birthday conference at Hyderabad.
Yeah, I had to run away from there, but yes.
Hello, Jyotsna.
Hello. How are you?
Very good. How are you?
Hello, Jyotsna.
Yeah.
Hi,
Good to see you.
Jyotsna. Hi, Kaushik.
Hi, Jyotsna.
Hi, Shahar.
Hi.
Hi.
Hi, Shahar. How are you?
Okay. It's a pity it's not in India, the conference. It would be nicer.
Yeah.
Maybe you can start, Bill. Is that okay?
Okay. Let me see if this
So-
screen share works.
So it's a real pleasure and an honor to introduce Professor Bill Goldman of the University of Maryland, College Park, USA. And he will be speaking on dynamics and classification of geometry on surfaces. Professor Goldman, please.
Thank you very much for the to the organizers and the scientific committee for the invitation. It's a great honor to speak at this conference honoring Raghunathan's birthday. What I'd like to describe is how the project in differential geometry, the classification of locally homogeneous geometric structures on manifolds, leads to some very interesting dynamical systems, both in homogeneous dynamics and inhomogeneous dynamics. And I'd like to survey some of the examples, some of the success stories in the classification of geometries. And then this leads to an interesting class of cubic surfaces and their automorphisms, which I'll finish with. So when I say a geometric structure, I mean a very special kind of structure, namely a locally homogeneous structure that is this collection of coordinate systems that are locally modeled on a geometry. And a geometry, I will mean in the sense of Felix Klein's Erlangen program, that it's the properties of a space invariant under a transitive action of the Lie group, namely a homogeneous space. The basic examples that I want to describe will be flat Riemannian metrics, which I'll think of as Euclidean structures, manifolds that are modeled on Euclidean space with coordinate changes, local isometries, hyperbolic geometry structures, metrics of constant negative curvature, and we can introduce singularities into the structures by allowing the coordinate charts to not be local diffeomorphisms, such as isolated singularities with specified cone angles. These are very important in the previous example of Euclidean structures, where translation surfaces or abelian differentials or quadratic differentials on Riemann surfaces have played a very important role, but I don't think I'll have much time to discuss that. Some of the structures that I will discuss include affine structures. These are the same as flat affine connections of zero torsion, but I want to think of them as being structures modeled on affine space with locally affine changes of coordinates. So these are like linear manifolds, if you like. And closely related are structures modeled on projective space, both real and complex. And since there's such a huge variety of flavors of geometries in homogeneous spaces, this is a very rich subject. So what I mean by classification is finding some moduli space such that the points parameterize the equivalence classes of structures. So the example that I like to give to non-mathematicians is that the two-sphere has no Euclidean structure. So there are many proofs of this fact. That means that there's no globally defined world atlas that preserves Euclidean geometry. So I want to fix a topological space, usually a manifold, say a real analytic or smooth manifold, and look at ways of modeling that manifold on, on a homogeneous space. So the example that I want to give, I'll come to this later, will be Euclidean space. We model it on Euclidean space with a group of isometries, and we want to find an extra structure of a marking, like in Bux's talk, which will be a topological coordinate system, which will the extra structure will give rise to a more tractable space. So that'll be the deformation space of GX structures on sigma, where GX corresponds to the action. And these actions will correspond to actions of the mapping class group of changing the marking. So the first example I want to give is quite familiar. Euclidean geometry is the geometry of Euclidean space invariant under its full group of isometries. I want to normalize the volume and choose an orientation to make the statement simpler. And then the topology I want to take will be the n torus sigma. And different Euclidean structures correspond to different lattices, and the quotients are the Euclidean manifolds. So in the deformation space, in the deformation space, that will be the space of lattices, but with the marking will correspond to a basis. So a marked lattice is nothing more than a basis of the vector space Rn. The deformation space is the space of marked lattices is just up to the equivalence relation of isometry, will just be the homogeneous space of bases of Rn under the special orthogonal group. So that's the symmetric space of SLNR. The mapping class group, which is this changes the markings, will just be the action of SLNZ acting on this space. And SLNZ will be acting properly on the deformation space. And therefore we can form a quotient, which is the locally symmetric space. And that's going to be the moduli space of flat tori. So this is a nice model for what I mean by a classification of geometric structures where the underlying topology is the n torus and the geometry is Euclidean geometry. Another example, which is not quite a geometric structure in my sense, but it's closely related by uniformization, is the classification of Riemann surfaces. And going back to Riemann, there is a nice space that parametrizes the Riemann surfaces of fixed topology. It's known that this Riemann moduli space has a lot of rich structure. It's not quite a manifold. It has some singularities at the symmetric Riemann surfaces, and that's true also for the preceding example of flat tori. A more tractable object is the Teichmuller space, and that consists of a marked Riemann surface. And that's a metric space, a complex manifold, contractible space of dimension 6G, real dimension 6G minus 6. A marking will be a diffeomorphism of the fixed topology sigma to the Riemann surface M. And we want to include this structure so that the Riemann surface can vary, but the topology of sigma is fixed throughout the discussion. Then the equivalence classes will then correspond to the mapping class group orbits on the Teichmuller space, and the Riemann moduli space is the quotient. So these are two examples where the classification is quite nice. The deformation space is contractible and easier to understand than the actual quotient, and this is one way of understanding the mapping class group and other groups, arithmetic groups that would arise as automorphisms of the topology. So let me briefly review what I mean by a geometric structure. The geometry is represented by the homogeneous space, X with a transitive action of G. The topology will be the manifold, usually a surface in this talk, and we'll have a universal cover and fundamental group, and the marking is a diffeomorphism of the fixed topology with the geometric manifold. The geometric structure will be defined by a coordinate atlas consisting of patches, defining local coordinates modeled on the geometric space, the model space, the homogeneous space, and then overlapping patches, the coordinate changes will extend to transformations in G. That can be unwound to give a map, which is a local equivalence from the universal covering space and a representation of the fundamental group by deck transformations acting now through G on X. The development global, the coordinate charts, and the holonomy homomorphism, the homomorphism from the fundamental group globalizes the coordinate changes. We would like to build a space, like a moduli space or a deformation space. And so we take a marked geometric structure, and I'll call that the deformation space. The association to the representation of the fundamental group defines a mapping from the deformation space into the space of equivalence classes of representations of the fundamental group into G. In general, these spaces can be pretty pathological. Anything that could go wrong can go wrong in specific examples, but the best cases, for example, hyperbolic manifolds, these spaces stratify into smooth manifolds, and this mapping tries to be a local diffeomorphism. Changing the marking corresponds to an action of the mapping class group, and the orbits, if the orbits will then correspond to this, whatever the moduli space is. However, generally the action won't be proper, and this will lead to an interesting class of dynamical systems. So the example I gave of the Riemann moduli space and Teichmüller space is familiar and fits into this framework using the uniformization theorem. Namely, the complex structures on a surface of higher genus identify with hyperbolic structures, and therefore the Fricka space, which is isomorphic to the Teichmüller space of hyperbolic structures, is now a model of this classification of geometric structures. The going back to work, I think maybe Andre Vey should be credited for knowing that the space of hyperbolic structures embeds as an open subset in the space of equivalence classes or representations, and the dynamical system is, as I mentioned before, proper, and the quotient identifies with the Riemann moduli space. In particular, the Euclidean analog, which is simpler for the torus, the deformation space of unit area Euclidean structures identifies with the upper half plane. The modular group GL2Z acts properly by linear fractional transformations, and one has a very nice dynamic. Dynamically, that's not very interesting, but function theory is quite interesting. I want to describe some examples now of where the dynamics is more interesting. Maybe it's worth mentioning that in the case of surfaces of higher genus and projective structures, say manifolds modeled on the real projective plane and their group of collineations, then we also get a nice quotient. But this is actually rather exceptional. If we look at structures on a 2 torus, then the Oliver Bowes proved that the deformation space identifies with the Euclidean plane, but the action of the mapping class group is the usual linear action of GL2Z. Let me say a little bit about these examples, which I think deserve to be better known. All the Euclidean structures are equivalent under the relation of affine isomorphism, because they all correspond to different lattices, and lattices, a marked lattice is a basis, and the change of basis defines a linear conjugacy between the two actions of the lattice. So the origin will correspond in our description of a complete affine structure on the torus, which happens to be Euclidean. The others, though, are obtained by conjugating by a diffeomorphism, and the diffeomorphism is about as simple as it can get without being affine, namely it's quadratic. And the pictures at the top of the screen show how this quadratic diffeomorphism bends the lattice and changes it to a new one. And these structures, I think, go back to Kuiper around 1950. Specifically, if you conjugate by this diffeomorphism, a simple and pleasant calculation shows that the quadratic terms introduced by phi cancel out, and what's left are the cross terms, which define an affine transformation. Now, the linear action of the mapping class group of the torus, which is GL2Z, is quite chaotic. It's no reasonable quotient. On the other hand, the Euclidean area is invariant. It follows from Moore's ergodicity theorem of 1966 in homogeneous dynamics that the action is ergodic with respect to this area. So every invariant function is almost everywhere constant, and almost every orbit is dense. However, there are plenty of discrete orbits, for example, the integer points inside Z2, and all the other rational points where the denominator is bounded. So the dynamics is quite complicated, and we wouldn't really want to take a quotient like the moduli space of flat tori or the Riemann moduli space. So let me say a little bit about general properties of this of these moduli spaces. That in the case of when the fundamental group is a surface and the surface is oriented, then there's a natural symplectic structure on the space of equivalence classes of representations. In particular, the symplectic structure in the case of a closed surface will restrict to the symplectic structure arising from the Weil-Petersen-Kähler structure on the Teichmüller space. Now this is on the space of hyperbolic structures, and this will also be defined on hyperbolic structures where we allow certain singularities and enter other connected components of the space of representations. In the case of compact groups, for example, the unitary group, the symplectic structure, the natural symplectic structure, to my knowledge, was first discovered by Narasimhan in 1970, where he wrote down a formula in terms of flat connections and differential forms. And later this played a key role in Atiyah and Bott's structure description of the moduli space of flat unitary bundles in terms of stable holomorphic vector bundles over Riemann surfaces, which Narasimhan and Seshadri developed from a more algebro-geometric context. And so this generalizes the symplectic structure on the Jacobi variety when n equals 1. In the remainder of my talk, I'll mainly describe what happens when the surface has boundary. In that case, the space of equivalence classes of representations, sometimes called the character variety, inherits a Poisson structure, and the Casimirs, the invariant functions, will correspond to fixing the conjugacy class of the representation around the boundary. And the fibers, the symplectic leaves, will be the symplectic manifolds upon which the mapping class group of the surface will be acting. So I'd like to describe, here's a few, I'll mention a few general principles. First, the components of the space of representations are, when G is a compact Lie group, are indexed by the elements of the fundamental group of the derived subgroup. So if G is semi-simple, then this is the fundamental group is finite, and the connected components are indexed by these, by elements of its fundamental group. This is also true for complex semi-simple groups as well. The mapping class group action will be ergodic on each component of the, when G is compact, of the representation variety. I had proved this in the case of SU2, and then later this was generally proved by Doug Pickrell and Eugene Zia. Particularly, ergodicity implies a statement about representations of the mapping class group that only the only vectors that are fixed under the mapping class group are the constants. And that's a more general fact, is that these actions are weak mixing. The only finite dimensional invariant subspaces inside L2 are the constants as well. When G is non-compact, a lot's known. It seems reasonable to expect that the actions are ergodic in all the components except for the component that Andre Bay identified as the Teichmüller space, the Fricka space. And recently, Marché and Wolf showed that in genus 2, there are 3 types of components: the maximal components, where you have a proper action, the ergodic actions in the other components, the Euler class 0, which corresponds to representations into PSL2 are the lift of the universal cover. They're actually two ergodic components. The main technique for proving ergodicity is to use the symplectic geometry and to show that the Dane twists are similar to Hamiltonian flows defined by looking at length functions and trace functions on the variety. So I think in the remaining part of the talk, I'd like to describe one particular example that leads to some very interesting and very concrete dynamical systems, and in particular, some affine cubic surfaces defined over the reals. So the topology that I want to take will be when sigma is the one-hole torus. So in this case, the fundamental group is a 2-generator free group. I'll be looking at the space of representations of that fundamental group in SL2C. There's a very nice answer which goes back at least to 1889 in a paper of Vogt, which says that the character variety, the space of equivalence classes of representations of the fundamental group, is given by an affine 3 space. It's given by, its coordinates are very simple to write down: the traces of the 2 generators and the trace of the product. You can think of this as a very algebraic version of the side, and angle test for congruence in non-Euclidean trigonometry, whereby the free group of rank 2, you can be thought of as a index 2 subgroup in a free Coxeter group of rank 3, and the fundamental domains, if you like, for structures correspond to triangles. In that case, the angles of the triangle, or dually the lengths of the sides, will correspond to the traces of these generators. But we're interested in the case of the punctured torus, and in that case, the boundary is given by a commutator, and the trace of the commutator is given by this rather fascinating cubic polynomial, which I want to discuss. The Poisson structure has a very nice formula. You take the Euclidean volume form, or its dual, and you take the inner product with the differential of the boundary trace, and you get this object which represents the dual to the area form on the level sets. So we want to look at the level sets of this, and I'm now going to restrict to the real points. So K is real, and the 3 variables are. The symplectic structure on the level sets, now when the parameter is less than -2, these correspond to hyperbolic structures on the torus with 1 hole or a puncture. And the Weil-Petersen symplectic structure is given by this formula. The Narasimhan-Atiyah-Bott structure for SU2 arises when the parameter is between -2 and 2. And one has to look at certain components because even for those, there's going to be representations. And yeah, I should mention that the real points in the character variety correspond to representations into the 2 real forms, SU2 and SL2R of SL2C. Why should this cubic polynomial have such automorphisms? Well, it's easy to see that they're given by natural involutions as follows. This is a cubic polynomial. Its restriction to each coordinate line is quadratic. In other words, fix two of the variables, you get a quadratic polynomial. And if you know one root of a quadratic equation, then you know the other one by a simple substitution. And that corresponds to the three generating deck transformations of the coordinate projections. So this defines a free Coxeter group of three generators. And this is a very interesting example of inhomogeneous dynamics, as you'll see. I should maybe mention that these are affine cubics. This, because the polynomials are not homogeneous quadratic polynomials, they don't extend to the projective space, and the automorphisms of the projective cubic will be a finite group. One particular case where you have singularities is when the level is k equals 2. These correspond to the reducible representations. And in this case, you get a rational parameterization of this cubic surface, namely corresponding to the eigenvalues of the matrix. So you can upper triangularize or diagonalize the matrix. Then the A and B parameters correspond to rational coordinates, and the traces are given by these simple rational functions. In this case, the action of the mapping class group, which is GL2Z, is going to be just acting on product of 2C stars modulo the natural involution defined by inversion. And here's a picture of what this cubic surface looks like. Another case that's been studied corresponds to hyperbolic geometry. And so this case, the level is -2. The structure is going to be a hyperbolic structure on the punctured torus. So these will be finite area, complete hyperbolic structures. Notice that the origin, when x, y, and z, psi, eta, and zeta are all equal to 0, that corresponds to a point. And that corresponds to the quaternion representation by Pauli matrices in SU2. So as I mentioned, the representations, the equivalence classes, the character variety, the GIT quotient is corresponds, the real points correspond to representations in the two real forms. You have the origin, which is the SU2 representation, and then SL2R representations comprising these 4 components. The reason you have 4 components is that these are now representations into SL2 rather than PSL2, and you have 4 different lifts. The Markov equation, which is I wrote at the top, corresponds to hyperbolic structures on the once punctured torus that have special triple symmetry. When the parameter is greater than 2, and this is the example that I'll end with, in that case, you get an ergodic action on whenever the parameter k is less than 18. But when the parameter, the trace of the commutator, becomes 18 or gets larger, then you get wandering domains. And where does this come from? Well, the fundamental group is a 2-generator free group. That's the fundamental group of a one-hole torus. And every homotopy equivalence of the one-hole torus is homotopic to a homeomorphism. That's similar to what happens for closed surfaces. But it's also the fundamental group of the 3-hole sphere of a pair of pants. And a homotopy equivalence from a one-hole torus to a pair of pants defines an embedding of the Fricka space of hyperbolic structures on a 3-hole sphere into this level set. And the first place this occurs will be when all three of the boundaries of the three-hole sphere are mapped in unipotently. And in that case, that corresponds to the finite area structure that has character 2, 2, 2. And in that case, or -2, -2, -2, and that corresponds to where the trace of the commutator, which is now a non-simple curve that intersects itself, self-intersection number is 3. That curve has its traces will be 18. So that's the breaking point, where the dynamics bifurcates. Here's a picture of the level set, which is a quite fascinating object. In that case, I drew the 24 straight lines, which can be interpreted as flow lines for some of the Hamiltonian flows. And there's certain points called Eckart points where 3 of the lines come together. And those points are exactly where that corresponds to these hyperbolic structures on the thrice punctured sphere. But now you apply elements of the mapping class group to change the marking and you get an orbit, which is discrete, but the action is ergodic. Once the parameter becomes larger than 18, then you have hyperbolic structures on a 3-hole sphere with geodesic boundary, and those will correspond to wandering domains. So it looks like a Kleinian group where you have islands of wandering domains, and then on the complement, the action is quite chaotic. So that's an example of what I think is a interesting dynamical system arising from the classification of locally homogeneous geometric structures. And I think this is a very rich and fertile area of investigation. And so I'll conclude here, and I'd like to wish Raghunathan a very happy birthday. Thank you very much.
Thank you very much, Professor Goldman, for a great talk. Thank you. Are there any questions? Hello? Hello?
Oh.
Can you hear me? Hello?
Yeah, you can hear.
Yeah, okay. So, Will, how much of this is expected to be general? I mean, this is given by one parameter that you're varying, right? I mean, so
right.
If it's a twice punctured torus, how much of this is supposed to go through? I mean, are there 2 parameters and at some?
Well, it's I think it's pretty closely related to a talk we heard earlier today by Books and outer space.
Yeah.
That the mapping class, that I'm just looking at the mapping class group of fairly simple surfaces, but you can't really avoid looking at out of FM.
Wow.
Because the fundamental, in general, the wandering domains are going to be permuted by out of FM, and there should be a correspondence with outer space, and it'll be very complicated. It looks very complicated, and the 2-hole torus looks like the first case where this should be really intriguing. Also, the five-hole sphere is another place where you'll have a rank 3 fundamental group. So it's only going to get more complicated.
Okay. Okay. Thanks.
I'm finding that just looking at this level set when k equals 18 to be quite fascinating itself. And there, the mapping class group is SL2Z, and that's going to be the building block. But part of the reason for looking at surfaces with boundary is that these are the building blocks for closed surfaces and more complicated ones. So this will be the start.
Thank you.
So are there any other questions?
I put some question in the chat.
Okay. Yeah. Okay, some of us will take a look at that.
Okay, I don't know what a Gelman matrix is, but the Pauli matrices are the ones that correspond to the I, J, and K quaternions.
And unitary basis also, Schwinger's unitary basis or unitary basis arising from Latin squares and Hadamard matrices.
Yeah,
They are projective representation.
maybe we can discuss it in chat. Yeah.
Okay.
Do that. Yeah.
Thank you.
Yeah. Thank you so much, Bill, and we will meet again at 7:50. Yeah? Thank you. Oh, hi, David.
Hello.
Hi.
Hi, David.
What is it? Is it good morning for you or good afternoon?
It's good morning. I'm in California
Okay,
now.
good.
I'm in Berkeley, so it's quite early in my morning. But
Okay.
We're going to have something for you soon.
yes, I in the 20 minutes I've been awake, I have read your email but not replied to it, Bill.
So Jeff and I will prepare something for you. Wasn't as bad as we were expecting.
Yes, I may have scared people unnecessarily on that one. There was only really one contribution to that volume where there were weird errors introduced at the proof level, but there really was one and it scared me too. So should I share my screen or?
Yes, please. So maybe I'll just make the introduction, then you can start. So
okay.
I'm very happy to introduce Professor David Fisher of Indiana University, Bloomington, USA, and he will be speaking on arithmeticity, super rigidity, and totally geodesic manifolds. Professor Fisher.
All right, now I have to remember how to get this. There we go. Sorry, that took me a second. I first want to say that I'm honored to be here and speaking this morning at this conference in honor of Raghunathan, who is one of the great heroes of the area of mathematics in which I've spent my career working. And I am only sad that we cannot all be together in Tata for this occasion, partly because I've never been and would love to come sometime. All right, so as Venki said, my talk is on totally geodesic submanifold, superrigidity, and arithmeticity. And I'm going to start by stating a slightly strange form of the main result, just to allow me to motivate some history. So I'm going to let X tilde be an irreducible symmetric space of non-compact type with no Euclidean factors. I'm assuming this is one of few places where I can say this and not be too concerned, but it will be specified to real hyperbolic space for much of the talk, so don't worry if it's not something you like. X will be the quotient of that by some group gamma, some discrete group gamma that has finite volume, and we will assume that gamma is irreducible or that the quotient is irreducible. And again, don't worry if these are words you don't like. You can think of a finite volume hyperbolic manifold if you prefer. And now the theorem that we proved is in some sense the following. It says if X contains infinitely many maximal closed totally geodesic submanifolds of dimension at least 2, then this group gamma is arithmetic. And now I should, for the students in the Zoom, maybe run over some of the definitions in this theorem. The experts already know them. Maximal is what you think maximal means naively, which is just it's maximal if it's not contained in another object of the same kind. So a totally geodesic submanifold is maximal if it's not contained in another proper closed totally geodesic submanifold. This is just to avoid stupidities. It's it's important that you make this assumption, but it's just to avoid certain examples. And as I said before, you can always think that X tilde is hyperbolic space if you prefer. Then results will really only be new and real and complex hyperbolic space. And you can also think of this theorem the other way around, which is important for some purposes, which is instead of thinking of it this way, you can think that, well, if gamma is not arithmetic, then we only have finitely many maximal closed totally geodesic submanifolds. And sometimes it's better to think of it that way. And just the other reminder is that G, which is the isometry group of X tilde, is a semi-simple Lie group. Gamma in G is a lattice, i.e. a discrete subgroup of finite covolume. And arithmetic means that there is some number field K, so that gamma is commensurable to the integer points over that number field in G. And of course, I could be more pedantic and insist, that there was some K form of G such that this was true, and the experts can bother me about such things, and those who aren't deeply already schooled in them would not get much out of my being more pedantic at this moment, so I won't be. The experts know what I mean. The non-experts should think, oh, I'm just thinking about the integer points, the Z points in G, which I'm thinking about, perhaps naively as a matrix group. All right, so as I said, this theorem stated this way is not really our theorem in some sense, because a lot of it follows from work of other people. And I'm just going to start by telling you some of that history, because it also inspires both the result and the techniques. So if X has higher rank, which in this context, I can say if X tilde contains a totally geodesic copy of R squared, then Margulis already proved in 1974 that gamma is always arithmetic. There's some history of that result as well as some contributions of Raghunathan's that I don't have time to dwell on today. But we'll start history in 1974. If X is quaternionic hyperbolic space or the Cayley hyperbolic plane, then correlating Romo-Shane also proved that X is always arithmetic, or really I should be saying here gamma is always arithmetic in the definitions I gave, but that's okay. So what's left of the theorem after you take their results for granted is that the theorem is about real and complex hyperbolic manifolds of finite volume. And for us, this is important. You know, there are theorems in this context where you could give a proof for a general X or X tilde. We really need the specific structure in the proofs in various places. We need these to be real and complex hyperbolic manifolds. And this, in that context, and really in, you know, the history of this is also a bit complicated. This answers a question that was asked by Alan Reed and Kurt McMullen in various forms in the mid-2000s. You know, maybe we're answering a question that's slightly more general than what they answered. But I mean, we're answering a question that's slightly more general than what they asked, but they more or less raised this question. And one of the key motivations for this is Margoulis's commensurator superrigidity and arithmeticity theorems, you know, the first of which is, you know, there's this superrigidity in higher rank, there's this superrigidity and arithmeticity theorem for groups with dense commensurators, which I'll talk about in a moment. And the key observation here that makes this, you know, theorem plausible in the first place is that if the commensurator of gamma is dense, then if I have one totally geodesic submanifold, I get infinitely many. And so I just want to explain these last two sentences a bit. I think it's on the next slide. Yep. So let's say that G is the isometry group of this X tilde, and gamma is the lattice. And then we let the commensurator be the set of elements of G such that when I conjugate gamma by G, I get a group whose intersection with gamma is finite index in both gamma and the conjugate. So, you know, this is the definition of commensurator. You know, it's that the conjugate has finite index both in gamma and in the conjugate. And Margoulis's other theorem also proved at the same time in 1974 is just that if the commensurator contains gamma at finite index, then at infinite index, then gamma is arithmetic. And actually the converse came earlier and was due to Borel, and sort of the example is, you know, if we take everyone's favorite lattice, at least in this room, which is SLNZ, and we look at its commensurator in SLNR, what you get relatively easily is the Q points in that group. And so this is an example of infinite, you know, of commensurator that contains the group at infinite index, and this is clearly an arithmetic group. And, you know, Borel's proof requires more work than this one observation, but this is essentially why it's true. And, you know, all of this, I find this somewhat hard to understand from the algebraic viewpoint, so I like the geometric one better. And that is that if G commensurates gamma, then G is an isometry of a finite cover of X, right? The covers of X have isometries that come from deck group elements. And what this is saying is that somehow we get extra isometries at finite covers that come from the commensurator. This fact is an easy exercise in covering space theory to check. And so now I'll tell you Reed's idea of why dense commensurator implies lots of totally geodesic submanifolds. We just pick one up. We pick up a totally geodesic submanifold in X. We lift it to a cover X prime, some finite cover X prime, where some element G in the commensurator is an isometry. We push M by this isometry and we push it back down to X. And it's a more or less trivial exercise to check that when you do that, you get a new totally geodesic submanifold. So any totally geodesic submanifold in the presence of dense commensurator gives rise to infinitely many And in fact, the easy exercise that I forgot to state is that once the commensurator contains gamut infinite index, it's not hard to prove that the commensurator is in fact dense. And that's easier to prove than it is than its arithmeticity is to prove. But so you have density here, and therefore you can move this around in lots and lots of ways once you're in this setting of being arithmetic and having dense commensurator. So I want to give a little more history, and this is probably the funniest thing that's happened to me in my mathematical career is this problem had been around for a while. I only learned of it in 2016. In the summer of 2016, I learned of it from both Agel and Stover, probably 3 weeks apart. Both of these guys told me this problem, and nothing was really known for a really long time. And then in 2018, with a slightly different author list with Lafont instead of Bader, we proved some first cases of this, where really what we proved is that the Gromov, Piatetsky, Shapiro examples of hyperbolic manifolds of non-arithmetic hyperbolic manifolds had only finitely many totally geodesic submanifolds. And really at essentially exactly the same time, Benoit and O didn't prove this, but they also had in at least the three-dimensional case, there was a key ingredient in this proof that they discovered independently at the same time. And they probably would have noticed it. It implied at least the three-dimensional case of our result, without my pointing it out to them relatively quickly, had I not pointed it out to them. And then in 2019, with Bader, Miller, and Stover, we proved the real hyperbolic case. And again, more or less at the same time that Margulis and Mohammadi proved the three-manifold case. We were, I think 4.5 weeks later to the archive than they were. The works were independent. But I've never encountered competition in my life before mathematically, and this was happening routinely on this problem. And then in 2020, we proved the complex hyperbolic case. And again, there it's a little, they did again beat us to the archive, but it's clear they'd heard talks about our work before they archived theirs. Baldi and Olmo proved special cases of this result, as well as proving a number of other interesting theorems. And this one is perhaps the most interesting bit of competition, because while everybody else on this slide is probably familiar to everyone here, Baldi and Olmo are doing this using, Olmo has some homogeneous dynamics contributions too, but they were really proving this theorem in their cases of this theorem entirely by different methods, using algebraic geometry, O minimality, and Hodge theory. And so it's very interesting that the theorem has two different proofs from entirely different worlds at that in those cases. And now, rather than dwelling on the rather intense competitive environment I lived in for 3 years while working on this, I want to talk to you about a little more longer view of history about why we care about totally geodesic submanifolds and hyperbolic geometry, and more context for these results. And so the first use I know of totally geodesic manifolds and real hyperbolic geometry is that the very first examples of real hyperbolic manifolds of dimension n with positive first Betti number in all dimensions were due to Milson, and he very much used the presence of totally geodesic manifolds. He even used the fact that there were a lot of them, and used various versions of the same tricks Reed was using in the observation I gave. Before that, there had been finally many earlier examples of manifolds with this Betti number, but those were also all built. Those were all built by Winberg as reflection groups, and again exploiting the. In a reflection group, you have the mirror of the reflection, and the mirror of the reflection is a totally geodesic submanifold, and will end up closing in the quotient. And so Winberg was again exploiting totally geodesic manifolds. Of course, in the context of any conversation about arithmeticity, the really important thing that occurred was in 1988 in work of Gromov and Piatetsky Shapiro, where they constructed infinitely many non-commensurable, non-arithmetic hyperbolic manifolds in all dimensions. And they did this by a cut and paste construction along totally geodesic submanifolds. So, you know, totally geodesic submanifolds played an important role in hyperbolic geometry. And variants of these Gromov-Piateski-Shapiro manifolds have been discovered and discussed and used for various things by numerous authors. I list here only Agel and the Seven Samurai, which isn't even, you know, really listing anyone, because I don't know if that's the way in which Saki Galander refers to his paper with 6 co-authors whose names don't fit on the slide, but I don't know. I hope it means something to many people. My favorite application, recent application of this trick is the Galander-Levitt theorem that says that in a very precise sense, most compact or finite volume real hyperbolic manifolds of dimension at least 3 are non-arithmetic. And in part of why I like this theorem is because combined with our theorem, it says that most compact or finite volume real hyperbolic manifolds have only finitely many totally geodesic submanifolds. That, you know, most of us, you know, grow up in this arithmetic world, and therefore by this observation of Reed, you might think totally geodesic submanifolds are common, but the finiteness is actually what's generic. And I do want to dwell for a moment on a couple of questions that I like, that I don't think are fashionable enough. And in fact, that I think people are oddly dismissive of sometimes. But the first is this question that's in the Gromov and Piateski-Shapiro paper, where they ask, are all real hyperbolic manifolds of high enough dimension built from subarithmetic pieces? The quotes are around those two phrases because those are their phrases. I don't want to ask a vague question on my own account, but I feel that Gromov and Piateski-Shapiro have the right to ask vague questions. In particular, they don't define subarithmetic piece in their paper, although in context, one has a sense of what they mean by it. And I want to point to a much more concrete version of this question that I don't know the answer to and that I think should get answered, which is, if you look at a non-arithmetic hyperbolic manifold of dimension greater than 3, all the examples we know of currently contain a totally geodesic submanifold of codimension 1. Is this because it's a fact or because we don't know a construction? I think that's an important question, and I find it very hard, you know, maybe high enough dimension should not mean bigger than 3, but I find it very hard to make sense of their question without asking this one. This is a question I think deserves research, and I think most people who study hyperbolic manifolds come from the school of Thurston and therefore tend to think the answer to this question can't possibly be yes, because it's not yes in dimension 3. But the reasons for that don't persist in dimension 4 and higher. I think it's a very mysterious question. And the reason this question is open is because all the examples of non-arithmetic manifolds we can construct above dimension 3 are variants either of this GPS construction or of reflection group constructions. I'm going to skip over the next 2 remarks on the slide about reflection groups. I was just surprised when learning these things for the purpose of this project that, you know, there are many, many more things about reflection groups that we don't understand than that we do. As a young person, or even as a middle-aged person, I was naive and thought that was a well-understood theory, and it is not. I do now want to say something about complex hyperbolic manifolds. This is the first time I've ever proved a theorem that's actually, you know, when you're proving a theorem, you're often thinking of finitely many examples, but in this setting, I was proving a theorem about, at this point in history, finitely many examples, because there are only 22 known examples of non-arithmetic complex hyperbolic manifolds in dimension 2, and there are only 2 known examples in dimension 3. The early work on this was by Mostow, Deline, and Thurston, who had 3 different points of view, but really gave overlapping constructions of the same examples. I think this 17 is wrong and is actually a 14, for which my apologies, but they found most of these examples in the 80s. I don't want to put on the slides the long list of names I should for all the other people who have worked on this since then. There are, now these 24 examples. All examples can be built, as I understand it, by all three of these methods. They all are, all the methods somehow find the same examples once you push on them exhaustively. And this question isn't mine, but is one of the more important questions in the field that I feel I can't talk about complex hyperbolic manifolds and arithmeticity at this length and not mention it, which is, just the question is, are there any non-arithmetic complex hyperbolic manifolds in dimension greater than 3? This question is actually related to the one about real hyperbolic geometry on the last slide, just in the sense that the reason why we can't answer the last question and why we can't answer this question are in some sense the same, which is that, we'd like to play games of cutting and pasting along totally geodesic things in the line of Gromov and Piatetsky-Shapiro. And if we can't do that in the complex hyperbolic world because all totally geodesic things are codimension at least 2. And so, the reason we can't construct more real hyperbolic manifolds might be the same one that we can't construct more complex hyperbolic manifolds. But it isn't, it isn't clear if that's a real reason or just an obstruction to our imaginations. And I do also want to mention another recent result by Asnalt and Grushunig that says that, all complex hyperbolic manifolds are integral. This means that, the matrix entries have to be integers, even if they're not all integers, as in the arithmetic case. This is definitely not true in the real hyperbolic world by work of Hegel and Belopetetsky-Thompson. But it's an interesting phenomenon where complex hyperbolic geometry is very different than real hyperbolic geometry. And I just want to, say a few more words about complex hyperbolic geometry because I want to be able to say some words about proofs and have definitions of some objects handy. So in complex hyperbolic geometry, I have, complex hyperbolic k-space sitting in complex hyperbolic n-space, but I also have real hyperbolic k-space sitting in complex hyperbolic n-space, in this case, up all the way to dimension n. These are the totally geodesic manifolds, or rather they're universal covers of what I'm talking about in my theorem. The CH1 is the hyperbolic plane, but in CHN, its curvature is -4, whereas if I took H2 sitting in CHN, it would have curvature -1. And, the isometry group of CHN is SUN, and the H2 orbits are SO21, while the CH1 orbits are SU11. And so, this is some picture of the geometry in terms of subgroups. And if I want to talk about the proofs are all done in language of dynamics and ergodic theory. The frame bundle of HN is SON1. This is its isometry group. And so if I look at the frame bundle of my compact or finite volume X, it's G mod gamma, where G is SON1. And totally geodesic submanifolds come from orbit closures of the subgroups of the form SOK1 acting on G mod gamma. And you should notice that SO11 is the diagonal matrices, gives the geodesic flow, and so orbit closures of SON1 are the geodesics. But they're the ones we don't like to think about because we want to mention at least 2. For CHN, as I said on the last slide, life is a bit more complicated. SUN1 is the bundle of complex frames. And, we can take this group W to be SUK1 or SOK1. So we have this group W in either case, which, I'm just going to let K be a variable or fix K and maybe fix the form in advance. But, this group W is going to be given to us to build totally geodesic submanifolds from. It's orbit closures for this group W. So we're always going to be studying orbit closures of W on G mod gamma. And And really, what we prove might be better formulated. The question was asked in terms of geodesic submanifolds, so that's how we state the theorems, and it's natural in that form, but you can state everything and talk about everything in the language of homogeneous dynamics as well. So if we have W acting on G mod gamma as above, we call an orbit closure maximal again if it's not contained in a larger proper orbit closure. And the theorem then really just is the form that, if there are infinitely many maximal W orbit closures in G mod gamma, then gamma is arithmetic. This theorem is the same as the other theorems. It's just, formulated in dynamical language instead of geometric language. I do want to mention that the question motivated by Gromov and Patetsky-Shapiro in that form becomes, if n is greater than 3, is it true that minimality of the action of SON minus 1, 1 on SON1 mod gamma, does that imply that gamma is arithmetic? Maybe it's better to think of it from this point of view than the geometric one. I don't honestly know, but I like this question, so I'm advertising it twice. Is there a question? So I now want to take the remaining few minutes to say something about proofs, because I am speaking to an audience containing many experts. And the first lesson in the proofs is the lessons from the master, which is what we learned from Margulis in 1974, which is to prove arithmeticity, we prove superrigidity. At the time, this was surprising, but by now one should know that this is a technique one should use. So from now on, G is a simple group, and really G should maybe be SON1 or SUN1. Gamma is a lattice. We have some other algebraic group over some other local field K. And superrigidity provides criteria for when homomorphism from gamma to this other group, and we assume there's a risky dense to again avoid stupidities. When does a risky dense representation extend to G? And what Margulis really proved is that, for certain triples, L, K, and rho, having superrigidity implies arithmeticity. And he didn't have to state things with this specificity because, well, he could prove superrigidity for all L, K, and rho essentially, but you really only need some of them to imply arithmeticity. And that's important here and has been important in other applications of this philosophy in the past. And the technical words are you only need L with the same complexification of G, or L absolutely isogenous to G, if you like that word. So from now on we'll be assuming this, but I'll try and be more concrete in what I say. And so I will at least get to state our superrigidity theorem, which is true just for these G's. The L's you have to care about are basically SOPQ and SUPQ. I'm missing some examples this way, but the experts can figure out what they are, and the non-experts would not find it enlightening. And now, we have this totally geodesic manifolds coming from orbit closures of W on G mod gamma, where GW is some simple non-compact group. And what the theorem says is that if I pick up one of these L's, it's going to come up in my proof of arithmeticity, and I look at any non-compact Zariski dense image representation of gamma into L, this extends to G, provided that for one of these W's and some algebraic subgroup J of L, there's a gamma equivariant measurable map from G mod W to L mod J. This is a slightly strange theorem to have, but it's an interesting theorem to have that might conceivably have other applications. It tells you that, there's some kind of map between equivariant measurable map between varieties that allows you to extend your representation. And that turns out to be enough to prove arithmeticity with. And now I officially have 2 minutes left. And I want to use those 2 minutes and maybe one more to give you some indication of the proof and maybe teach some students some bits of history at the same time. There are 2 steps in the proof. One step in the proof to prove arithmeticity is, well, I better build this measurable map. If I'm going to use this theorem that requires it, I should build that. And then we should study the properties of equivariant measurable mappings between algebraic varieties of this kind. This entire philosophy is, in some sense, the same philosophy that Margulis used in proving his superrigidity and arithmeticity theorems in the 70s. The stranger part from the point of view of the history is that building this first measurable map, for this we use homogeneous dynamics and study measures on projective bundles over G mod gamma. And step 2 uses ergodic theory of actions on algebraic varieties. I want to just put down the parallel to Margulis's original proof, where we started there with a gamma equivariant map from G mod P to L mod J instead of G mod W, where P here is a minimal parabolic subgroup. Here, step 1 is very easy from the modern point of view. It was harder at the time, perhaps. But from the modern point of view, this just follows relatively quickly from amenability of P. And the strange thing happening here is that this W is not amenable, and therefore there's a lot more work in step 1. And the second step, Grisha used, the fact that the group had higher rank, and some facts about centralizers that derive from that. And he used the ergodic theory of actions on algebraic varieties in a way that, very much inspires the way we're using it, although there have been some significant historical developments along the way. One of them, which I don't think is the most important, but is important to mention just because in rank 1, you clearly can't use centralizers. Groups just don't have interesting centralizers in rank 1. So instead, what we get away with is we get away with using normalizers. If T and G is a subgroup, the normalizer is also a subgroup, and we use structure of normalizers of groups to prove our theorem. I don't know, am I out of time, or do I have another minute or two?
There is no one else to come, so you can continue. So
there's no one else to come, so I can continue. And I'm early in my morning, so I'm just waking up. So I could talk for much longer, but I won't. I want to mention something more about the proof, particularly in the complex hyperbolic case, just because it's an interesting connection. This is some sort of vague outline of the strategy. I should mention here that the way in which we do step 2 uses very much some earlier work Botter did with Furman, where they were basically just trying to understand, the proof of step 2 in Margulis's proof is very short, but not very comprehensible in my mind. I've had many students ask me, what's really going on there? How did he come up with that? And Grisha, when I've asked him, has told me that it's he realized there was a fundamental incompatibility between measure theory and algebraic geometry. I think that is what drives that proof, but Botter and Furman have been thinking about ways to repackage and re-understand that proof for many years now, and I think it has been fruitful. In the complex hyperbolic world, our proof doesn't sort of continue to smoothly follow the lines of Grisha's original proof, even modified. We encounter some kind of obstruction. And from this obstruction, we build a geometry preserving map from the boundary of complex hyperbolic space to itself. And geometry preserving here just means we send the boundaries of complex geodesics of CH1s to the boundary of CH1s. And I just wanted to mention this because, the history of geometry preserving maps is another thing that in rigidity theory has a long history. Probably most famously, Mostow's use of Tietz's theorem to prove the higher rank cases of Mostow rigidity. That work was then extended to prove QI rigidity by Kleiner and Lieb and Eskin and Farb and Eskin. With my student Nguyen and with White, we used the same set of ideas to prove some QI superrigidity theorems. The thing we're actually using here is much closer to these works, where they use the same kind of geometry preserving map to prove various results about superrigidity for maximal representations. This is work of Berger-Yotzi, Pozzetti, and Duchenne-Licora-Pozzetti. And we really are using very explicitly in our work a theorem of Beatrici-Pozzetti. The other interesting thing is that Margulis and Mohammadi, they used a geometry preserving map to prove their version of the real hyperbolic case. In the real hyperbolic case, we could get away without that. But then when we tried to finish the complex hyperbolic case, it came back. And so perhaps I should end there and just say that, you know, there are lots of interesting questions left here about both superrigidity theorems, arithmeticity of manifolds, and geometry preserving maps of symmetric spaces, which have, you know, some set of relations. Thank you so much for your time and attention.
Thank you so much for a very interesting talk. Thank you. Are there any questions? Hello, are there any questions?
Venki, is it audible? Can I?
Yeah, you are audible to me.
Okay. Yeah. So David, did I miss something? But in this collection of examples of non-arithmetic lattices in CH2, CH3, are there? I mean, do there exist totally geodesic complex one-dimensional gadgets at all?
Yeah. Yes, there are. Well, that's an interesting question. They're built from some sort of reflection group philosophy. And because they are, there will be some totally geodesic submanifolds. When I was in progress, when we were in progress on this work, I asked the same question to Rich Schwartz because I wasn't sure. And I asked him if, you know, if knowing this about finiteness of totally geodesic manifolds was interesting, and he said he thought yes, but you know you could try and prove this theorem by a different method. Although the different method, it's interesting that that's hard too, right? You could look at these 24 examples, and you could find it just, you know, they're very explicit groups at this point in history. Most of them we know presentations for. You could try and build them and then look for totally geodesic submanifolds, check that there are only finitely many in each of the finitely many examples, and be done with it, not need, you know, methods that are very much transcendental, which we're using. That turns out to be hard as well. It's actually genuinely hard, even given a very explicit example where you can find a few totally geodesic manifolds to show that you found them all. Right? It's easy to find some, and I believe in all the examples, it's easy to find some that are sort of handed to you from the right point of view on the construction. But then you want to prove finiteness. I mean, this was the other thing. I had a funny experience. The first time I talked about any of this, I was talking about the paper with Lafont in front of Shmuel Weinberger, and I was giving some introduction with some motivation, and Shmuel blurted out at minute 3, he said, "What about the Gromov, Piasecki, Shapiro examples?" To which I replied, "Well, that's the theorem, right? You know, even just for those simple examples where you clearly have at least one totally geodesic submanifold, you'd think there might be some naive, easy hyperbolic geometry, you know, soft geometry topology, you know, linear group proof of the finiteness." And you know, even in that case, our proof uses, you know, some non-trivial homogeneous dynamics. It's, you know, none of these things are you know, finding a few examples of mirrors that come from the constructions isn't that hard, but proving that all there is not, you know, there are no explicit examples where there's an easy proof of, say, okay, I'll hand you this manifold built this way, and you'll hand me back an easy explicit proof of finiteness. That typically doesn't happen. There are you know, there are two graduate students of Stover's who have in fact done that for some cusp hyperbolic 3 manifolds, but that happened after our work, and I still don't know a way to do that even for a compact hyperbolic 3 manifold.
Okay. Yeah. Thanks. Yeah.
So other questions or remarks? Well, let's thank David again. Thank you very much. Yeah.
Yeah. I have some
Raghunath.
comments. Yeah.
David,
Can I-
Raghunath wants to ask you.
Yeah. Can you hear me?
Yes, I can hear you.
Yeah. Okay. You know, if you start with the Gromov separate example, you have two arithmetic groups which are non-isomorphic. I mean, even after commissurability and so on, and they're patched together along a submanifold. That's how the whole thing is constructed. Now, these two arithmetic groups in SYN1 gives rise to these two arithmetic groups come from some Q structure, and then you can go to Q root minus 1, and there you get natural unitary group SUN1. From SYN1 you go to SUN1, and you can easily construct such a group with in such a way that you get the same group when you go to SUN1. Though there are two Q structures on SYN1, but when you go to QI, you can manage things in such a way that you get the same unitary group. Okay, in SUN plus 1, if you like. You have two groups of which are over R SYN plus 1, and they have a common subgroup which is SYN1, and that SYN1 group gives you a SUN1 group, which embeds in SUN plus 1, and you can assume that the SYN plus 1 groups give the same SUN plus 1 group. Thereby, you get a discrete subgroup of SUN1 on the one hand, and a non-arithmetic discrete group of SUN1. And you can look at the group generated by this. My hope was that this would give you a non-arithmetic lattice. I didn't succeed in proving it, but this was my hope. I think I managed to prove it was discrete, but that it's a lattice is not so clear. This is long ago, so I might have made a mistake in my proof that it is discrete, but I was hoping that it is discrete, and the group generated will be a lattice. So this was one of the ideas I had. Maybe someone else has also thought about it and thrown it out as not possible. I don't know. So
no, I actually we found this suggestion of yours on a problem list, and I don't remember who we was, and was talking with someone, and they found on a problem list from some conference the same suggestion you just made attributed to you, and so I too have played with this idea of yours, and yeah, it would be great if it was a lattice, but I also could not prove it.
Okay.
Excuse me, can I ask a question?
Yes, of course.
Yeah, I'm Sengupta Venki.
Yeah, hi.
Hi. Yeah, so you raised that question about existence of codimension 1 totally geodesic submanifolds in higher dimensional hyperbolic manifolds.
Yes.
So there you assume that they are all non-compact?
No, the question is for finite volume, including the compact case.
Including the compact case?
Yeah, including the compact case.
No, the reason I'm asking is in the first talk today, Hio told us she was working with compact hyperbolic manifolds, and she showed that the image of a horocycle is a codimension 1 totally geodesic submanifold. I mean, she can correct me if I've understood her statement wrongly.
No, not totally geodesic.
It's not totally geodesic. The horocycle is not totally geodesic.
No, not horocycle. U orbiting G mod gamma, the image inside the hyperbolic under the projection. She showed
it's
totally geodesic submanifold of codimension 1.
It's the closure of the horocycle, not not the horocycle itself.
Not the horocycle, the projection onto G mod, K mod,
No,
gamma.
the projection of the closure, not of the horocycle.
Okay, okay, the H orbit you mean.
Orbit closure and then project.
Yeah, I don't know what she said, and she doesn't seem to be here right now. She's heard this talk before, so. But I've talked about this question before. I'm quite sure if she knew the answer, she would have told me by now.
Okay.
She and I have talked recently, and she knows I'm interested in this question, and we've talked about it. So I don't know what she said, but I don't think she knows the answer to this question.
No.
At least she didn't
It's
last
Amir
week.
here.
No.
I don't think that's what she said. She said the closure is always a properly immersed manifold, which is always true. That's.
Yeah, must be.
Okay.
Otherwise, that would have answered.
No. Totally geodesic submanifolds of codimension 1 cannot exist even for arithmetic lattices, unless they're the specific type of SYN1 with even over the number field. No, those which come from division algebras, quaternion division algebras, they cannot have codimension 1 totally geodesic submanifolds. That's out of the question. If I understand right, that's your question, right, Sangupta?
Yeah, but probably Amir just said, probably she just showed it was a totally immersed codimension 1 manifold. But I thought she said something about totally geodesic.
There is no assertion about codimension. It's just a manifold. You might not have any totally geodesic one. The closure can be the whole thing. You can have. That's all she said.
Oh, so the manifold is not totally geodesic, simply a codimension 1 thing.
No, there is no assumption about the dimension. It's always properly immersed submanifold, but you don't know what the codimension is. Maybe it's the whole thing. Typically, it's the whole thing.
I see. Yeah, I was getting confused with this thing. Thank you for clarifying.
Sure, thank you.
If there are no other questions, let's thank David again, and that closes today's program.
Hi, David. Good to see you.
Good to see you too.
Hi.
Hello, Professor Ramnan. How are you?
Oh, hello. Hi.
Nice to see you.
Hi,
Hi, everyone.
Hi, Ramana.
People only show their faces after the talk is over.
That's good, right?
Meeting all of you.
Hi, Rama.
Hi, Ramana.
Hey. Oh, hi, Ramana. Very nice. Nice to see you.
Hello, Amir.
Hi, how are you?
Good. How are you?
Good.
Hi, ready.
Thank you.
Yeah.
Great to see you. Hi, Shakar. Yeah, too early here.
Yes, it's the earliest in my morning I've ever given a talk. It was less difficult than I thought it was, actually.
That's good. Yeah.
Hi, Safa.
I'm gonna go have some coffee.
Oh, hi, Grisha. Nice.
Okay, so see you tomorrow.
You're sitting in your office or home, Shahar?
I'm at home.
Okay. Okay.
Oh.
Oh, yes.
Okay. Back.
Hi, Nimish.
Hello, Nimish.
How are you?
Good. Good to see you. My video couldn't start for some reason. So yeah. So, hello, Rama. Hello, Raghunathan. Hello, Professor Gopal Prasad.
Hello, hello, Nimish. Where are you?
Oh,
In
hello,
Columbus
Grisha.
or where? Where are you?
Hi, at home.
At Columbus.
Yes.
Okay.
And you are in
I'm in New York.
New York?
Yeah, with Anoop.
Oh, really? Nice.
Yeah, Anoop and Ila are all here. So, 11
You're
of
in New York
us.
or Princeton?
We are not going to Princeton this time because Indu had a knee replacement surgery. So
I see.
she is recovering here.
Okay.
Yeah.
Ramanan, you are muted. You said something.
Yeah. How long will you be in New York?
Oh, I am going to be here until at least end of this month, maybe early next month.
Hmm.
Oh, are you going to travel?
No, I have been at home for more than a year now.
Yes, none of us have traveled, but what about
That's true.
you coming to visit your daughter?
Yes, we have to see when it is possible.
Yeah. So actually, Ila met her recently. She invited her to her house, and it was a very good meeting.
Very nice.
Yeah.
I met her last February.
Yeah.
She came here she managed on the next day the flights were cancelled.
Oh.
We went back.
Yeah.
She got in this IIT Distinguished Alumni Award.
Yeah, she is
So that
very.
is why she had come, and she left. So I went to Bombay and I was with her. And then I left her at the airport, and then the next day it was cancelled.
She is doing very, very well.
Apparently, yeah. Since
Yeah, no,
you don't know.
I am very happy to hear that.
Yeah. I am equally happy. So.
Yeah, sure.
How is Gopal?
Pardon me?
How is Gopal?
I am Gopal.
Oh dear. It is Medha Prasad.
Yeah, it says Medha. Medha is my granddaughter. Since I am in New York, I am using her web.
Oh God. This is Gopal. I thought it was Deependra.
No,
Deependra had gone to New York. Yeah.
No, I am here in New York with Anu.
Oh, good. Oh, okay. Now I understand. Yeah.
Yeah, so thank you for your telephone when I was recovering. So that was nice.
I know. I know we have been in touch, but somehow the looks were deceptive. Yeah.
Yeah, maybe it's a darker room. So yeah. Very good to see you.
Yeah, good. Same here.
Okay, folks, I'm leaving the meeting. Bye-bye.
Yeah, sure. See you tomorrow.
Good to see you all.
How are you, Madabusi?
Bye, Suri. Hi, Suri.
Hello.
Oh, hi, Suri. Bye.
See you tomorrow.
Hello, Suri. How are you? Okay, so.
How are you, Suri? Doing fine?
You are muted, Suri.
It got muted again by itself. I'm fine, thank you.
Yeah.
How are you now?
Often I hear about you from my grandson.
So he's going to ETH, right?
Yeah, he is going to ETH, yes.
Okay, good night.
Good night.
Bye.
Good to see you all. And then I will see you tomorrow.
Okay.
Yeah.
Bye. Yeah, again.
Take care. Take care.
Bye.
Bye.